well. Okay, that's good. So, welcome to the 5-day COMSOL training course, which focuses on optical modeling. We are more or less going to talk about wave optics, not specifically with the optics module, but the wave optics part of the modeling. So, the COMSOL, if you see the product suite, it has optical modeling can be done by wave optics, ray optics, as well as RF. RF being a very old module, which actually can do a lot of things that wave optics can do. So whether if you have RF module, this complete course can be done with the RF module. But only the last day, when we talk about the ray optics part, at that time you might need this ray optics module. But most of the time, we are going to either work with RF module, and we are going to just touch upon the additional feature with wave optics module. So wave optics module is also kind of a very important part, but there's a huge overlap between RF and wave optics module, as you will see as the course progresses. The only additional benefit that the wave optics give is the modeling of very long dielectric structures using the beam envelope methods. Okay, so there are a lot of features, a lot of applications that um, someone can do with optical modeling in COMSOL. For example, optical fibers, waveguides, scattering, photonic crystals, laser cavities, multiphysics analysis like stress optical effects, propagation of beams. It could be a Gaussian beam, it could be an orbital angular momentum beam, coupling of various types of waveguides, plasmonic effects, nonlinear effects like second order, third order effects, grating and metamaterials, or the optoelectronics, which is again a part of multiphysics analysis. Okay, so let us straight away kind of go to COMSOL and start setting up a single simple model. So I assume that all of you guys are interested to model optical physics in this model, and that's what is the aim of this course. So what we'll be doing it to, if you're kind of very new or very experienced person, the what this course is going to talk about is the best practice approach. Okay, so that's what I have learned with the last 7 years, not last, but I have joined another institute before working with COMSOL. So in the 7 years of what I have worked with COMSOL, um, there are a few best practice method that I have learned, and that's what I would like to share with you guys. If and this course is going to be complementary to the online course that is already available. I'm not sure if you have seen that course or not, but if that course you have seen and gone through that course, it would be always good. So let me just see that. Okay, this is the day one of the course, but similar to this, there are day five. 5 days are there. So I will share this along with you guys so that you can go through this course as well. This is the with the iSTEM ISC course that we conducted 2 years back. Okay, so we are going to take an alternate approach for this course. A little bit more we will be adding in this course, which will help you to take it forward. So the basic part is explained in this course, and then we will try to take about the other complementary features that we have not talked about in that particular course. So whenever you are trying to model optical physics in COMSOL, the first thing is to model the electromagnetic wave propagation in air domain. Okay, for example, you have a cube structure like this. Okay, and your objective should be first, whether you are experienced or a kind of a beginner person, is always to go through step by step, right? And the first thing is always to model this as air domain. Okay, so you you can create an air box, a rectangular box of geometry, assign it as an air material, and then your objective is to propagate electromagnetic plane wave. So you want to, and you start with a kind of a normalize the electromagnetic wave propagation in normal direction, and then you can think about at another angle of inclination. And so this is what we will be doing. So here you can see that if I keep this as x, y, and z, so can anyone tell me what is the direction of polarization of this electromagnetic plane wave? So this is the electromagnetic plane wave. If electromagnetic plane wave propagation, this is what we're going to try to understand. So can you tell me what is the polarization direction? Anyone? I hope you can see my screen, right?
Is that negative Z direction?
Okay, so this is,
Yes.
yeah, there are two things just to make sure that there are, the first thing is polarization direction, and another is propagation direction. So does that change your answer?
Yeah, sorry. Then it is
XY, X-axis.
XY. No,
Okay, sorry. Yeah,
Y
I,
direction.
It's an
okay,
X-axis.
yeah,
Y axis.
सही वाला पेन दो यार जल्दी पेन दो
yeah.
सही
So
वाला
is
मुझे
it Padam Priya Ranjan who is speaking, or there are multiple people who have unmuted? So, sorry, it was Padam Priya
Uh, yes, sir,
Rajan.
but I was wrong. It's I think it is on X direction.
Okay, yeah. So it's actually in x direction. So how it happens is that you have electrical field
Yeah.
polarized in this
Yes.
direction, and its propagation direction is what?
That is negative Z. I hope.
और that is Z
Correct,
axis.
correct, correct. Yeah. So this is in x direction. So you can write plus or minus x,
Yes.
because you will see is that it's actually propagating in both the
Yes.
directions.
Yes,
So
sir.
it will oscillate in both the directions. So it will first oscillate in positive x direction, and then it will oscillate in minus x direction, right? And then again it will move towards plus x direction, right? So eventually it's polarized in x direction, and its propagation direction is in minus
Z.
z direction, correct? Yeah. So we are going to set up this simple model, and the way we model in COMSOL is that because it's a mathematical tool, we have to put boundaries to our geometry that we are going to model, right? So eventually what we're going to model is an air domain which is kind of um, towards infinite in all the directions. So for example, this all the sides are towards infinity. Okay, these things are kind of very important, because eventually you're going to apply some kind of constraints, right? So all the sides uh, are actually extending to infinity. Okay, so but actually making such a big domain is kind of very difficult, because as you will see in some time is that there's a limitation of the mesh size, and because of the mesh size you cannot actually model very big domains, especially with optics, electromagnetic wave propagating in these optical mediums, right? So we need to terminate our domain. So this domain that you have marked in red color is the actual modeling domain. Okay, and then I'm terminating it with some kind of boundaries from the sides on the walls, and through that I'm trying to propagate my electromagnetic plane wave. So there are no reflection because of the termination. Okay, so that's kind of is kind of very very important when we try to model. Okay, so let us start this approach in modeling of electromagnetic plane wave propagation polarized in x direction and propagating in minus z direction. Let us start to do this simple step, and important part is that this is in 3D. Okay, so this is in 3D. Okay, so if you see the video that I shared sometime back, it was in 2D, right? So if you are learning, you are very new, so you always start with 2D. Okay, so in the 2D model, it's the same thing. What I have shown over here, it's the same block that you see over here. Okay, same block like this. Okay, the only change that I've done in that video that I've shared some time back is that instead of modeling the 3D geometry, I have been modeling the 2D cross section of the geometry. 2D cross section means this geometry, so this plane in the center. Okay, okay, so you can see that this is the 3D geometry, and this is the 2D geometry. Okay, so you're actually trying to move from 3D geometry to 2D geometry. Okay, so that's what you can keep on changing from 3D to 2D geometry based on your requirement, um, but both of them are kind of very different. For example, um, if your 2D geometry is something like this, so you have an air domain, and inside air domain you are making a one circle. Okay, so this is the 2D geometry. So can you tell me, if I translate this into 3D geometry, how will it geometry look like? So this is a kind of a rod, nanorod, for example, having the diameter of around 50 nanometers, for example. So any guess what it will look like in 3D geometry? You can unmute and answer, anyone.
Sir, if it's a
Well,
nanorod, then maybe the 3D it will be a cylinder, or on the other hand, if it's circular, then it can be a sphere as well.
Okay, so it would be so in 3D it would be either a wire or a sphere. Okay, anyone else?
yeah,
Hole,
same
or
sir
else a
in
hole, or
3D.
else a hole, sir. A cube
Hole.
block with a
Okay.
hole.
Okay. Yeah, yeah, correct, correct. So that depends upon which material we actually choose. So
Yeah.
it depends on the material. So whether it is a vacuum or anything. Yeah, that's true. Yeah. So actually, how it looks like in yeah. Anyone else want to add anything? I think it was Chetan, and who else was there to discuss? Sorry. Yeah, that's good. Yeah. So basically, how it looks like in 3D, it could be actually translating to something like this. So if you model this in 2D, right? So it will translate to 3D in this kind of structure. It would be always a cylinder. Okay. And what you do is that you actually take a cross section in the middle. Okay. So you actually take one cross section in the middle. So that's how it translates into this one, right? So whether it is a sphere in the center or a nanorod, um, both of them will have the same cross section, right? So but if you model in 2D this kind of geometry, it will always translate into a rod. It will never be translated into a sphere. Okay, so just be careful about when you model in 2D, because you need to always make sure that how it
Uh,
actually looks like in 3D.
Hello, Tom. I have a question.
Yeah,
Yeah,
is it
my name is
it is
Faraz. My name is Faraz.
yeah, hi Faraz. Yeah.
Yeah, so I have a question that you mentioned that whenever we translate into 3D, it will transform into a rod and it will not transform into a sphere or sphere. So, what is the reason that it will always translate into a rod?
So you want to know what is the reason why it is always
Yeah,
translating? Yeah, yeah.
yeah.
So basically, if you see, that's a very interesting question. So I just kind of making a small jump, and just to show you. So don't worry about what I'm doing little bit quickly. Just to okay. So for example, you make one geometry like this. Okay, and I make one circle in the center. Don't worry about the dimensions that I'm putting right now. Okay, so this is the geometry that I've made now. Okay, so we have a rectangle, we have a square, and then we have a circle in the center. Okay, so here you can see that when you go into electromagnetic wave frequency domain, um, you will see that there is something known as three component vector, out of plane vector, in plane vector, right? So what does it mean is that this kind of structure that you have right now, it's actually a cross section of some kind of a 3D structure. Okay, so you can see that um, the only cross section of the actual geometry which would result into this one could be either this one, or it could be like, if you see, if it like this one, right? If you have this, you have this, and a sphere inside, right? So both of them actually can actually result into this. But in COMSOL, uh, here actually you cannot see the thickness over here. So ideally you will also find the thickness over here. So that is the out of plane thickness. I think it would be available with other physics, but it's not available in this one. But uh, how do I explain? Means you actually the COMSOL actually understands that this structure is going to infinity in inside the plane and outside the computer surface. Okay, you understand what I'm saying?
Yes, yes. So by default, console understands that the vector is going from like from on our screen. It is going outside towards the
Yeah.
screen and also on the back side, right?
Exactly, exactly. Yeah. So that's it's not in our control. It's
Okay,
how it works. So
okay,
so yeah. So yeah. So sometimes we may think that if we have a 3D structure like this and we can actually make a model like this in 2D, which is do we get the same result in 3D, right? But that's not the true kind of modeling that we are doing. So it will always represent this kind of a rod structure. Okay,
okay,
so we
okay,
should be always careful because COMSOL will actually extend this geometry into in plane and out of plane direction. So yeah,
okay. And
that's how it will.
if we just want to extend it in plane, not out of the plane, then console cannot do it, right?
Sorry,
We
can you
cannot.
come again?
Yeah, yeah. So as you mentioned, as we understood that console by default extends it in out of the from the out of the plane, like
Yeah,
backwards
yeah, yeah,
and enter. But
yeah. In
if we
front.
want to extend it only backwards, or or vice versa, or towards or towards inside, like
Yeah.
towards my face, only
Hmm.
towards my face. That this is we cannot do it in
Yeah, I know. So
console.
actually, what is happening is that it doesn't it's the same thing. If you see, for example, you model this structure over here, right? And
Yeah.
then what you are saying is that I extend towards the
Yeah.
inside, but it's towards infinity. So
Okay.
it's
Okay.
a
Okay.
modeling towards infinite. So it doesn't matter
Yeah.
whether it extends
Mm.
toward any side. Okay,
Okay.
so
Understood.
it's
Understood.
towards infinity. So yeah, it doesn't
Okay.
matter. So ideally, it assumes that it is the cross section of an infinite. So in our 3D geometry, this could be finite actually. So this geometry, this dimension could be finite, right? It could be, for example, 50 nanometers or 100 or 500 nanometers, for example, right? But this simplification assumes that the out of plane thickness is infinite. Okay, that is just to reduce the complexity of our uh, mathematical modeling of Maxwell's equations. So it
Okay.
reduce the one dimension, and with that it kind of significantly reduces the degree of freedom with which you can do it quickly. So it's kind of a simplification that we do with
Okay.
2D modeling.
Okay. Okay. Thank you.
Okay.
Thank you.
Okay, yes, looks good. So any more questions?
Yeah. Hello.
Yeah, yeah.
So I
Please
am not
introduce,
sure
because
in.
I don't know actually. Yeah, yeah, you can please introduce, because I don't
I'm
know
Sujay.
your name at least. You're
Sujay. Yeah.
Sujay. Okay, yeah,
Yeah.
Sujay. Yeah.
So I'm not sure about COMSOL, but in Autodesk, so similar 3D geometry tool, you have an option to define your radius as a variable, and you can then say that as you move out of the plane or inside the plane, keep reducing the radius to
Okay,
a
okay,
exponential degree. And if you do that, then changing then moving in plane and out of plane will result in the sphere rather than a rod.
okay. I see. Yeah,
So that is an
that's
option in
interesting.
Autodesk.
Hmm. Okay.
It is
Mm-hmm.
an extension of the extrude function, ext
Okay, I see. I
RUD.
see.
But I'm not sure because Autodesk
Hmm.
function is a completely different, and this is a different thing. But
Correct. Yeah.
it looks sort of similar in the when you open this. It is a 3D geometry part,
Yes.
but I'm not sure. So COMSOL, I can't say. But anyway, so it was
Yeah.
just.
Mm.
But
No.
for physics,
Yeah.
it won't make much sense to extend it
Yeah,
to
I
a
understand.
sphere.
Understand. Yeah. Yeah. But yeah,
But thank
that's
you.
a very interesting thing actually. Yeah. But with COMSOL, I have not seen still people
Yeah,
doing.
it might be true. I'm just saying
Mm.
that
Yeah.
mathematically,
Yeah.
they
Yeah. No,
do
that
have
that
this kind
really
of.
makes sense actually. Yeah. That is
Okay.
really interesting. Um, yeah. But yeah, right now that is not kind of thing possible with COMSOL as of now. Yes. That's good. Any more questions anyone have with
Yes,
this?
sir. Hello.
Yes. Yeah. Your name, please?
Hello, sir. This is Nadeem Ahmed.
Nadeem. Yeah.
Sir, suppose we have an infinite array of plane of holes in a surface, like we do in EOT.
Okay.
Next, suppose we have infinite hole, periodic holes in a surface, and
Mm-hmm.
what do we do if we want to eliminate that that plane by a plane wave source? We apply a periodic boundary condition. So by simulating one hole only and applying the periodic boundary condition, we can get the entire idea.
Mm-hmm.
So is it even possible to further reduce that? For example, we by simulating only quarter of that hole or the half of that hole, because in some software I have seen, but I was not that expert or familiar with those software, and I try to find that in COMSOL, but did not get anything from that.
Mm-hmm. So have you seen that nano hole array model of COMSOL?
Yeah,
Uh,
yeah, yeah. Yes.
okay, yeah. So again, it's kind of a very tricky question to what you've asked. So it actually depends on how far the holes are. For example, okay, just hold on. Is anyone trying to join? Okay, yeah, looks good. Yeah. So basically, if you have kind of a substrate, a dielectric substrate, and there are holes. For
Mm.
example, these holes like this, and there are kind of many holes. I'm not drawing all of them. Just
Yes.
trying to have a
It's
few
array
of.
of infinite hole, we say.
Yeah, correct. Yeah. So in the example model that we have in COMSOL, if you have seen, they have taken the whole structure. Okay,
Mm.
this whole structure they have actually taken from this side to this side, and then they are implementing a Gaussian Gaussian function, which is kind of acting as a laser source and hitting to this dielectric structure, plasmonic hole array example, right? So the so now your question is, maybe I will try to reframe your question. Is like, instead of modeling the whole structure, can you actually model only a single hole and give periodic boundary condition on both the sides?
So
Would
that's
you?
that's we do. That's a
Mhm.
common practice we do. We can do that. I
Mhm.
want to say that we can even can we even further minimize this
Oh,
geometry
okay.
by
Even
only
further,
yes
like this, you mean?
by only quarter or the by half of the whole, because in FTDT people do that.
Hmm.
Like that, they just simulate the quarter of the
Yeah, yeah, yeah.
hole.
No, no, you can do that. Yeah, 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 yeah. You can do that. So there are a few of the example. If you have seen this nanoscatter example, so in which they model only quarter of this gold nanoparticle. Okay,
Okay,
so
okay.
in that you have to be very smart because you have to play around with boundary condition because
Yes, exactly.
in COMSOL electromagnetic physics, unfortunately, there are no symmetry boundary conditions. Okay,
Yes, sir.
so in mechanical, you have symmetry boundary condition. Now, in symmetry boundary condition means that if I have a circle and I break my circle into uh, like four parts,
Mm.
okay, so I can apply symmetry boundary condition over here and symmetry boundary condition over here. Okay. So instead of this, I can model only a quarter of geometry,
Yes, sir. Yes, sir.
and here I can apply both the sides symmetry boundary condition. But
I think we don't have that condition in electromagnetic.
yeah, so we don't have symmetry boundary condition, but we have means COMSOL has boundary condition which actually acts very similar to a symmetry boundary condition. So that is actually known as PEC PMC.
Okay.
Okay, so this is PEC and PMC. Okay,
Perfect electric, perfect magnetic.
perfect electric conductor and perfect magnetic conductor. So that is depends upon how the electrical and magnetic fields are associated within the modeling geometry. For example, uh, okay, for example, my electrical field. So now, as we know, electrical field and magnetic field are perpendicular to each other. So we have the electrical field like this one. Okay, so we know that if the electrical field is associated like this in horizontal direction, the magnetic field, of course, would be in vertical direction, assuming the propagation is in the third direction.
Hmm.
Okay, so this would be the magnetic field. So if that is the case, then you can actually apply. Um, uh, you can apply which color? Yeah, so you can apply PEC over here.
And PMC on the other side.
Yeah, exactly. Here you can apply PMC.
Okay, sir. Thank you.
And then you can actually take symmetry conditions.
Yes, sir. So, the
Okay.
example what you were
Yeah,
suggesting,
I will
can
show you
you?
the example. Yeah, yeah. So if you go to COMSOL and then either you go to the model and application files, which is a good way to search the model files. And if you search nano scatterer, okay, okay, nano particle, okay, no, still no, okay, something like nano. Okay, this one, yeah. This is the example. Um, Optical scattering of nano gold
Okay, okay,
sphere.
okay, okay, okay.
Yeah, so
Oh,
here if you see,
hmm.
okay, here if I can also see over here, if it allows to open, wave optics module, and then we go to optical scattering and scatter. No, this one scattering
Okay, sir.
nanosphere,
Okay.
right?
Thank you, sir.
So
Thank you.
yeah,
I will try that. I will look it into.
yeah, yeah. So I'll just show you because this is kind of a little bit advanced, but still it's good. So here you can see that they have used. Oh, no, okay, now they have introduced this symmetry plane. So that's what again coming to
Yeah,
Ananda's
yeah,
point was she was asking why should we use 6.2 or 5.2 because in 6.2 now they have
yeah.
introduced something like symmetry plane, which is not
I,
a part of earlier.
yeah, it was not
But
the part of until 6.1.
yeah, so that is something good actually. I think, or they have written manually. I don't know. Symmetry PEC. Why don't I see? Okay, okay. Symmetry plane. But yeah, there is something new. The symmetry plane now they have
Symmetry.
added, right?
Yes,
Yeah.
yes, yes.
So this is symmetry plane. So that's interesting. Yeah. So this PAC or PMC, basically, it
It's the
makes the
same thing
cross
what you were
product.
saying.
Yeah, yeah. So just cross product certainly. But that's interesting. Yeah, they have done this finally. So
Yeah.
that's great. Yeah, yeah. That's good. So yeah. Any more questions? Okay, looks good. So if there are no more questions, let us go forward and try to go back to where we started our discussion and then digressed back. So what we are trying to do is we are trying to try to model the air domain, trying to propagate the electromagnetic plane wave polarized in x direction and propagating in z direction. Okay, so let us start that. So this is how COMSOL looks like once you start or open the COMSOL file. You can just click on the model wizard. So just quick raise of hands who are trying to do the model along with me. Can you raise hand? Oh, yeah, correct. Yeah, I can see this. Okay, good. It's a good number that we are trying along with me. That's correct. So the first thing is to open COMSOL and then go to model wizard. Okay, so COMSOL gives a multiple option of how you can make the geometry. Either you can make a 3D geometry, as I said, 2D axis symmetry, or 2D geometry, 1D axis symmetry, 1D and 0D as well. Right. So I already discussed about 3D geometry and 2D geometry. 2D axis symmetry is something like a ring kind of structure which you want to model, and can you actually exploit the circular symmetry of or angular symmetry of your geometry. Right. So what we're going to do is going to select the 3D geometry and then go ahead and go to optics. You can go to wave optics and you can go select the EWFT interface. Okay. Some of you might not have optics module, then you can go to RF radio frequency and choose the electromagnetic waves frequency domain. Right. But if you have the optics module, you can go ahead with electromagnetic wave frequency domain interface. Okay, just wait for a few seconds for you guys to add this. Okay, so I hope you are able to add this. So don't be get so overwhelmed by so many interfaces. So it's just most of the time we will be actually working with electromagnetic waves frequency domain. So don't need to be worried about so many interfaces. Okay, so okay, that's good. So I hope you have added electromagnetic waves frequency domain and then click on study. And in the study you need to again there are many different kinds of studies. Okay, so you can either use frequency domain or wavelength domain. Okay, so frequency domain is the most used study, but yeah, if you want to use wavelength domain, it's the same study, it doesn't change anything. Okay, then we have eigenfrequency analysis to know which kind of modes can be existing within a particular um, cavity, for example, or it could be an optical fiber. Okay, sorry, if it is optical fiber, then we do mode analysis. Okay, but if kind of cavity is there, then you can do eigenfrequency frequency analysis. Okay, so we'll choose wavelength domain and click on done. Okay, so just make sure that you have a cube over here. This cube means that it is a 3D geometry. Okay. Okay. So I hope you guys are along with me. Any challenges you are facing, just let me know. Okay. So the next thing is, as so now let me just give, because I see 80% are new to COMSOL. Just let me give a little bit of understanding of how the GUI of COMSOL looks like. Okay. So let me just add this over here. Can it add? Okay, it can. Looks good. Oh my god. Okay, looks good. So over here on the left hand side, yeah, on the left hand side, this is known as the model builder. Okay. The model builder is the section where all the settings nodes are placed. For example, the geometrical settings, your material settings, your physics settings, your mesh, the type of study, and then finally post process. Right. So the approach usually performed is from top to bottom. Okay. So you first make the geometry, you make the materials, then you add the physics, and then you keep on adding the kind of study, and then finally you post process the results. Okay, so this is the actual approach that people take. If you click on any of the node, you will see a settings node coming over here. Okay, so each settings can be changed once you click on over here, and then you come over here. So this area is basically for that settings node, change or modify the settings. Another way to move from to change the geometry and physics is the ribbon pane. So this in the top is the ribbon pane. Okay, this is the ribbon pane, and the approach that it follows is from left to right. Okay, here you can see is geometry, then materials, then physics, mesh, study, results, and developer node. This developer node is basically for uh, writing scripts along with this, right? So if you're interested to write your own script and do some kind of a batch processing or some similar lines, you can use these scripts as well. So on the right hand side is the GUI. Here all the geometry that you actually create comes over here. Over here is the very important part, which is the message, which tells you how much time the computation is not going to take me is taking, what is the degree of freedom of the model. So once you click on compute, it will compute degree of freedom, and based on the degree of freedom you can actually tell whether how much time it actually will take, right? For example, you can see over here the degree of freedoms, which was I was solving in some time back, it's around 72,000. Okay. Along with this graphics pane, you can also see there's also something known as convergence plot. So this convergence plot actually helps you to understand is your model converging or not. So there could be some kind of non-linearity which could result into non-convergence of your model, right? So with this convergence plot, you can actually see whether your model is going to converge or not. Okay. Okay. So any questions about the GUI? So basically, we have model builder, ribbon pane, and the settings pane and GUI. These are the main things within a COMSOL setup. Okay, I hope there are no more questions in the GUI. So let us start the important thing, that is to define your parameters. So one of the important parameters to define is the wavelength. Better not to define the wavelength with any terms like wavelength or uh, lambda, right? So because some of the parameters have been internally defined as those names, right? So better to define something like LD and not, right? So this is what we usually write. So once we write LD and not, you can write whatever the wavelength that you want to operate with. So for example, it is 600 nanometers. Okay, so I want to give an input as 600 nanometers wavelength. So this is my operating wavelength of my electromagnetic plane wave. Okay, make sure that you write your units in square brackets, otherwise you may face a problem. Okay, so just make sure that you always use square brackets. Okay, I hope you are able to add this parameter. So wavelength, operating wavelength is 600 nanometers. Next is to go to geometry, and in geometry you can change the length scale. Again, it's very important that you change the length scale because you're going to either work in micrometers or nanometers. So it doesn't make sense that you keep on working with meters. Okay, so you go to geometry 1 and change the length unit from meters to nanometers. Okay, I will wait for a few seconds for you guys to change the unit length. Okay, so I hope you have changed the unit length now to nanometers. It's very important that you change this geometry because otherwise some changes or if you forget sometime to mention the units in the geometry, then it kind of makes the geometry very concerning. Okay, so let us make a geometry of so I hope you guys are with me. Just a quick raise of hands. Okay, I see a few questions as well. Okay, I see. Yeah, looks good. So okay, so I see Kavita is asking about what do you mean by degree of freedom. Um, Degree of freedom is um, okay. So let me just I will come to a degree of freedom. How do you define it? Once you see the mesh, then it would be more easy to tell what is a degree of freedom, right? So let me just make the geometry and come to the mesh, and then let me define what is a degree of freedom. Okay, so okay, so in the geometry, you just need to right click on geometry, make a block, okay, and make the width to be about 300 nanometers, depth of 300 nanometers, and the height to be around 2000 nanometers. Okay, and I click on build all. Sorry, 2000, right? So just make sure 2000, and you can click on this zoom extents to actually watch the model, geometric model. So here the
Sir, can you repeat it again?
yeah. So the width is around 300 nanometers, depth is around 300 nanometers, and depth is around height is around 2000 nanometers. Okay, I right click on geometry and clicked on a block, and in that block I have added this dimension and just click on build all, and this geometry would be like screwed up like this, something like this. Okay, so you cannot visualize all of the geometry in a single go. To see that, you just click on zoom extents and you will see something like this.
Okay, sir.
So I hope you are able to make this geometry. Anyone facing any issues or challenges to make the simple geometry? Just yeah, just let me know if you have any challenges. I can help you guys. Okay, looks good. So I hope you are able to make this.
Hello. Hi,
Yeah,
sir.
yeah. Please, what happened?
Yes, sir. Actually, I'm not getting that convergence plot in my screen.
Okay, don't worry. Yeah, so this is what I've been doing something. So yeah, it can, but don't worry, it will come very soon.
Sorry.
You don't want that, but yeah, it will be coming very soon. Convergence is kind of a headache in some time. You will see that means especially with nonlinear
Okay,
problems.
sir. Sir, actually, I lost that first step which you thought. I have
Okay.
started from geometry. Before that, you thought something, but I was getting some problem here in my screen. Is it possible to repeat it?
So you are able to create this model with
Yes, sir.
3D. Have
Yeah,
you
I got it.
added the parameter?
Yes, sir. Parameters I have added.
Yeah. Did you go to geometry and change the length unit to nanometers?
Yes, sir. That one I have done. Before that,
Have you before that? Before that, I have not done some anything. So I have just added the parameter.
yeah.
Okay. And then
Yeah, here.
change.
Okay.
Sorry. Hmm? Yeah.
I missed
LD not.
this one.
Okay.
Parameters.
Yeah. So it's LDA
Oh,
naught, and that is around 600 nanometers. So what I'm saying is that the electromagnetic
huh.
plane wave that I'm going to launch is a monochromatic. It's like impossible to create it physically, but yeah, I
Huh.
assume that this is a kind of a monochromatic, perfectly deterministic monochromatic light source that I'm shining of 600
Okay.
nanometers.
Okay, sir.
Okay.
Thank you. Thank you so much.
Okay, that's good. That's good. So now you have added the geometry. The next step, as you see, is the materials. There are multiple ways to handle materials. You can just right click on the materials and add material from library, which is the most simplest way to move with. But if you have more experience, you can add blank materials and keep on adding material properties. So right now,
Sir, small now.
yeah,
Actually,
yeah,
for me, it's not showing block option in geometry.
it's not showing. What is not showing?
Block option. After clicking right click,
Right click on geometry, you're not seeing block. What options are you seeing?
I'm not getting, sir.
No, what options are you seeing if you right click on geometry?
1 minute. Wait. That import circle, ellipse, rectangular, square.
Yeah, if it's square, then means you have not used 3D geometry, you used 2D geometry. So this has to be 3D geometry.
Okay, sir.
Yeah. Anyway, so you can see this what I'm doing. You can do the see the recorded videos and do it because I think it will take time. So if you can make a new
Yes.
model with 3D geometry and do it. Okay. Okay.
Okay.
So I will add the new material. You go to build in and go to air domain. Can you? Yeah, let's go. So this is the built-in and air domain. Okay, just right click on the material, add a material from library, and double click on air. Anyone has a question? Dharma, have you a question? You have unmuted.
No, sir, it's done.
Okay, yeah. Otherwise, you can mute yourself so that.
Yeah, yes.
Thank you. Looks good. So, yeah. So I right click on materials, add material from library. So here there are a lot of materials, especially in optical domain, which I don't want you to go as of now because today is the first day. You can go to the built-in and double click on the air domain, and you will see that the air domain has been applied to the single geometry whatever you have added. Okay, I'll just close this air material domain, otherwise it will take my space of the GUI, which actually will become a little bit more complicated in some time. Okay, so I hope you are able to add the air material. Anyone facing any problem, any issue to add the material? You can just communicate through the chat box. That would be also good. Yeah. If you face any issue, just let me know. Okay, looks good. So the once you have added the air material, the next thing is to add the physics conditions. Okay, so I want to launch an electromagnetic plane wave as I discussed some time back like this. So people from intermediate experience. So can you tell me which boundary conditions do I need to choose? Any idea?
Scattering boundary condition.
So may I know your name, please? Sorry,
Jaya Krishnan.
Jai Krishnan. Okay. Scattering boundary condition. Anyone else?
periodic.
Sir,
Sorry.
sir, which in which side you are asking? In XY directions.
From the top, I want to launch. So this is the same thing that I want to launch. I want to launch an electromagnetic plane wave from top to
So
bottom.
we can apply port on the
Port.
top, port on
Okay.
and off
Uh-huh.
on the top and bottom.
Okay.
And the side we can use scattering boundary first and second order, or we can also use PML.
Okay. Yeah. Looks good. Anyone else want to add anything? Jansi, you have.
Sir, sides left and right, we can use periodic boundary conditions. Top and bottom port.
Okay. Looks good. Anyone else want to add anything? Yeah. So as you see, there are multiple ways of doing the same thing, of launching this electromagnetic plane wave. You can either use scattering boundary condition as well, ports, as well as terminating can be done with PMC, PEC, combination of PEC and PMC, or periodic conditions. Right. So most simplest one is to model using periodic port conditions and giving periodic conditions on the sides. Okay. So that's what we are going to do. Just before we start, it's worth to go through this physics module that we have over here. So here, if you go, you can see that there's something known as discretization. Okay, so by default, it has a quadratic type discretization. Okay, so at a later stage, I will show you, if you want to, if your modeling domain is kind of, it creates a significant number of degree of freedom, how you can actually reduce the computation time by increasing the discretization order and reducing the mesh size. Okay, so quadratic is by default selected. If you go to wave equation electric, you have the most important material model, which is electric displacement field model. So over here, by default in wave optics, it is selected as a refractive index. In the case of RF module, electromagnetic waves frequency domain, that is EMW, you will see that it is relative permittivity. Okay, and there are other options based on the specific sheet of the material. Either you will have loss tangent, loss angle, dissipation factor, dielectric loss, or any of these other dispersive material. Right, these three are the dispersive materials, so you can also choose that. Okay, by default, let us move with the refractive index, which is
Excuse me, sir.
the yeah, yeah.
Uh, Sir, what does it mean quadratic means?
Okay, I will show you. So there is something known as element order.
Okay, okay, okay. Equation, you mean to say?
uh Not exactly equation. Yeah, so this is a nice blog which I recommend you guys to see, because if you guys are doing a lot of COMSOL, uh, this shape elements will always keep in um, touch with you. For example, now let me just put it in a very simple way. Okay, now there are I have a track. Okay, a track, or kind of of a line, and I want to have a solution on that particular line. Okay, one of the simplest way would be to find the ends. What is the value of, at that particular line, what is the value of the function at that particular line? For example, it could be like, I know that it is, okay, maybe change the color. Okay, for example, the value at x equal to 0 is this much. At x equal to 1 unit, or maybe 10, it is this much. Okay, so now uh, what does the linear element do? Is that, oh my god, what is happening? Why it's rubbing? Yeah, so okay, let me just, yeah, so this could be the another value of x equal to 10, This could be the value. Now, the linear discretization, what it will do is that it will just put linear interpolation between this. Okay. Now you go to a higher quadratic. Quadratic, what it will do is that it will ask that I need three solutions. For example, it will again give you this solution. It will give you this solution, but in the middle there could be like a little bit higher solution, which we don't know, right? While we are solving. So what it is going to solve you is this solution. Okay. Now, if you go towards higher, even quadratic is there, then you go even higher. There is something known as septic, I guess, right? Quintic. Quintic is like 4 points it will give you. So this point, it will give you this point, it will give you this point, and it will give you this point. Okay. So actually, the curve will actually look something like this. You're able to understand what I'm saying?
Yes, sir.
Yeah. I don't know. It's you don't look so convincing, but uh, you understand. What's your name? Sorry,
Yes, sir. We are taking
Jancy, right?
multiple,
Uh,
yes, sir, multiple points while we are
yeah, correct.
trying to solve.
Hmm. Yeah, correct, correct. So which one would be the most accurate? What do you think?
Quintic.
Yeah. So as you go on increasing the order, it's becoming more accurate. But can you tell me
Yes,
what is the issue with those? Because ideally, if it is more accurate, then why don't we go for more like septic?
it is taking more time to solve more points, more
Correct. Yeah,
degrees
it's
of
going to take.
freedom.
Yeah, exactly. Yeah. So that's why you have to. This is a trade-off between the time and this element order, which we have to choose, right? So that's why people use quadratic. They have seen that with quadratic, it's very good. So here, the same thing what I was showing here. So if you see this, there are 4 points, and there are solution at the 4 points. So either it will show like this, and this. This is case of linear um, first order um, quadrilateral Lagrange element, but this is for a linear case. Okay. In the case of quadratic, one more point is added edge in the edge as well in the center. So it can show up to 9 different variations. Okay, and so on and so forth. Right. So the element order is kind of very important uh, in this. For example, you can keep on increasing the element order and reduce the number of mesh elements. Okay, that way
Uh,
actually you can trade off. Yeah, sorry.
my name is Faraz. I have a question, just a follow-up question. So, how, as a simulation engineer, as an engineer, how can we came to know that how we can decide that we have to go with quadratic or cubic or higher orders, or we should do higher order simulation or lower order simulation. So, how we can decide it?
Basically, the best way approach is to put it as default. Okay, the default is quadratic, so you keep it as the quadratic. Don't change it.
Okay.
Okay, people change only when they find problems, right? So ideally, that's how it goes with modeling and simulation. The best practice, you keep the default settings as what it is, because that's the most tried and tested version. Okay, so only if it is not working in life, then we try to change, right? So here also,
Okay.
if it is not working, the model is not working, and you are getting an error of out of memory errors, right? Then you try to change the quadratic, this discretization, to perhaps a very higher, for example, cubic,
Hmm.
okay, or
Yeah.
quartic, and then you try to change your mesh to a very poor mesh, right?
So,
So
okay.
then it,
Okay.
yeah, then you get
Thanks. Thanks,
it.
Utam.
Yeah, looks good. Yeah. Any more questions? Anyone? So Jansi, does it help your question? Your question was it able to
Yes,
answer
sir.
your question?
Yes, sir. Yes, sir. Thank you.
Okay, looks good. So basically, you can go through this blog as well to understand more about this discretization orders. But this is for little bit advanced people. If you are a little bit new, then you don't need to go into this all these things. Maybe perhaps if you face some kind of issue later on, then you can dive into this. Okay, that's good. So cool. Yeah. So I think Kavita has said about the same thing that Chansey was saying. That's correct. Now, as you have already said, let us apply port condition. So how to apply port condition is just right click on electromagnetic wave frequency domain and apply port condition, and I apply port in the top. Okay, so that's very important. That is, I apply port in the top, and then COMSOL gives you an option, a type of port. Okay, so the most basic type of port that you would like to work with, most simplest type of port that you would like to work with is periodic, no doubt. Okay, so periodic is the most simplest type of port that will give you some solution, which is kind of mostly accurate, because in most of the time in optics you model only a small part of geometry, right? And then you apply periodic conditions. What I mean is the following. Okay, as we were discussing some time back as well, uh, I have this structure which is made up of silicon. So this is made up of silicon in the bottom, silicon substrate. This is the air domain. Okay, and then we have nanorods. Okay, many multiple nanorods. Okay, so assume that this is a 3D geometry, even though it looks like 2D. I can just add something like this. So just assume that this is a 3D geometry. Yeah. So assume that this is 3D geometry. Okay. So now when you're trying to model this guy in COMSOL, um, you actually model it something like this. Okay, you made a 2D cross section, so it looks something like this. Again, this is a silicon structure, this is an air domain. Okay, and then you have the nanorods like this, so it's just above this silicon substrate. Okay, now if you model the complete thing, it is always going to be a little bit more time consuming, and people have already been talking about the time. So what they do is that instead of this, we model only a small unit cell. This is known as unit cell. Okay, this is a unit cell, and the good part of the unit cell is that you don't need to model the complete thing. You don't need to model the complete thing. You can only model the, you need to only model the unit cell. Okay, which means that it is still having silicon in the bottom, air in the top. Okay, and the gold nanorod or any metallic nanorod in the center. Okay, so you can see that we translate from the actual 3D geometry to 2D geometry. Okay, and then we move from 2D geometry to a single unit cell. It's still 2D geometry, but a unit cell. Okay, the good part of this is that it actually significantly reduces the time computation. Uh, in this, what we need to do is we need to apply periodic conditions on the boundaries. Okay. Okay. Right now, what I have done is I have still selected a 3D geometry, right? So in this case, if you see the video that I shared in the YouTube, it would be talking about a 2D cross section, but in this case, it's a 3D geometry. So we'll apply a periodic condition not only on the left and right, but also in the front and back as well. Okay. So any question about this conversion from 3D geometry to? Okay, so I hope it's clear. So apply port condition, and type of port is periodic over here. Wave excitation as on. This is important. On is very important. That means that I'm going to launch my port over here. Okay, this is also going to be very important for my scattering parameters, because it is actually a two-port network, and the scattering parameters that I will come in some time actually defines the transmittance, reflectance, and absorption eventually, right? How much power I'm going to launch? Ideally to put 1 watt if you are trying to only model the scattering parameters. Next is the polarization, right? So if you remember, the polarization is we discussed in the starting. Polarization is in x direction, right? So you see this is the x direction polarized, so I want the polarized to be in x direction. Okay, and elevation angle, azimuth angle, I want make 0. Okay, so no more changes. I just add change type of port as periodic. By default it will become on because this is the first port condition. Next is electrical field. By default it will be electrical field. You can also change to magnetic field, but it only changes the polarization.
Sir, I
Okay.
have a question. About the
Yeah.
so I'm Sujay. About the
Yeah.
boundaries.
Okay.
So boundaries, I understand it's like if you are modeling the air medium, then you are just taking a small chunk of it. Then the sideline boundary would be scattering of nature. But the type of port, why would periodic make sense? Because in this setup, you would have one port at the beginning and one port to terminate. Why would you need a periodicity there?
Yeah. So what right now I'm modeling is this geometry. Okay. I'm making a infinite domain of air
Correct?
on out of plane direction and left and right side.
Correct?
Okay, so one way is to use periodic condition. Another way is to use symmetric conditions. So both the ways you will see it's similar kind of as parameters that you will receive. What I'm saying is that it's this small unit cell is repeating towards right hand side, left hand side, back and front.
Yes, yes, I understood. But that is repeating is happening. Aha. So not only boundaries are repeating, but also ports are
Uh,
repeating.
Yeah, correct. So it's a
Okay.
complete chunk. It's a slab of air. You got
Okay.
assuming
Okay.
the slab
Correct.
of air, which is like I'm giving it electromagnetic plane wave. That is also infinite plane wave. So like
Correct.
it's everything is giving to slab.
Got it.
Yeah.
Thanks.
Okay. Any more questions? Anyone? Okay.
Sir,
Sorry. Yeah.
yeah, sir. Although I guess some of us here understand the boundary conditions, but uh, I think some of us are also very new. So, is it possible that you can spend a little time on how do you define? I mean, that by definition, what are boundary conditions and by definition, as in when you say periodic, how do you visualize it, or when you say port, how do you visualize it? Although we have a basic understanding, but I
Mhm.
think it will be better.
Yeah. Yeah. Yeah, definitely. So the port condition is the way why we use port is but I will give you kind of not exactly the mathematical description. I will give you the applicative definition, like why we use port. The reason we use port is to give, so port is kind of a source boundary condition. I want to launch a wave. I want to launch an electromagnetic chunk of energy, right? I can launch a temporal wave. I can launch a Gaussian wave. I can launch a temporal Gaussian wave. So if I want to launch some kind of an energy, electromagnetic energy, I use port condition, right? uh, how do you launch it? There are multiple ways, right? So basically, in optics you will either be working with periodic, um, or you'll be working with numeric. Okay, periodic is the most simplest way to start modeling, because with periodic, it becomes very simple. You just apply periodic boundary conditions in the end, and you just say that it's this slab kind of thing, and it kind of very easy to model with. You put any obstructions and you will get very good results with it. Just assuming that the obstruction that you are placing in the center, it's kind of repeating in all the sides. Okay. Uh, the periodic conditions that I was talking about uh, was this one. So the how do you define the periodic condition is that you will see that So you will see over here. So actually there is a, the geometry involves multiple obstructions, right? But I am modeling only a single obstructions, and I just make a unit cell, apply periodic condition. The only assumption that I'm making is that the scattering bounds, the scattering that this obstruction is going to create is going to be evanescent. It means that it's going to die down and it's not going to interact with my adjacent obstruction. Okay, so this is also going to create some kind of scattering, but this scattering is going to be evanescent, means it's going to die down before it interacts with the neighboring obstruction or nanorod or whatever is the central thing, right? So only if we assume that they are kind of very far apart, okay, only then we actually use the periodic conditions. So this should be like, this d should be like very many high as compared to um, the amount of evanescent period, means the time that it will actually die down. Okay, so that is something I kind of will come to you once you start modeling and other things. Okay, so yeah, so that's how with the definition part. Okay, I hope that helps. Yeah, looks good. So yeah, so we
Excuse me,
were
sir.
at, yeah, sorry, yeah.
Sir, port is, you said it is like source of energy. Can I imagine it is like some light coming and falling on the particle? Let's say laser light or something.
Yeah. So yeah, correct. So exactly, yeah, you can say that. Correct. Yeah. So it's kind of a light source that you are modeling um, on any nanoparticle or any substrate. Correct.
Okay, sir. Thank
Yeah.
you.
Your name? Sorry. Yeah.
Jansi, sir.
Jancy. Okay. Yeah. Looks good. Yeah. Looks good. That's good. So I hope you are along with me. You've added port condition, periodic port. So numeric port is when right now I am saying that it is polarized in x direction, okay, and propagating in z direction. So I know the polarization direction, but sometime based on the um, material properties of my conducting media, the fundamental mode may change. So if I want the fundamental mode to be understood and launched, so even fundamental mode or first order, second order, third order mode, higher order modes, then I use numeric port. But that is a little bit advanced. I'm not going to talk about today. Perhaps in later stage I will talk about numeric ports. But and we don't work with other type of modes like rectangular mode, coaxial, or circular mode. That is not what we use in dielectric structures. Okay, this kind of modes are specifically for RF guys. For example, coaxial cables are there, so you can launch this. If you have a rectangular waveguide like a what do you call uh, rectangular waveguide, right? Waveguide.
Like
So
a
if you
red
have
waveguide,
a copper waveguide, sorry.
waveguide, rib waveguide,
Yeah, no, not rib waveguide. So the rib waveguide is still
but a dielectric.
yeah, it's a dielectric waveguide. I'm talking copper waveguides, metallic waveguides, where you
Okay.
work with micro meter ranges, gigahertz application. So those are the things where we talk about rectangular waveguide, TE mode, TM mode, and other things. Circular is again with um, circular again you have uh, with it's actually with RF application. So basically with wave optics, you actually work with either numeric or periodic port. Okay, and you change this one. Now the next thing is to apply port in the bottom. Okay, so how do you do that? You can either add a new port or you can just right click on port and duplicate. This is the most simplest thing. Okay, just make sure that you remove this port in the top in my port 2 and apply the bottom part. So here it should be only one boundary. Okay, and type of port should be same periodic, but it should be off.
Sorry, sir. Just a question. Like, I don't know, like how this red. I'm Ayushi. So how
Hmm.
this red arrow is coming? I don't see it anywhere in my screen. I don't know.
Okay,
Uh,
yeah, because you're using 5.2 perhaps. I don't know.
Oh,
um, I don't know. Very difficult to tell. But are you using port condition?
yeah, I'm doing the
You're
same
using
as
port
yours, but
periodic port one. Okay.
yeah,
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 then you don't have because you have 5.2. So yeah,
sure,
so it's maybe it was not there by the time it was 5.2. 5.2 is like 5 years back.
sure, sure, sure. No
Yeah,
worries.
it's not there. But let us see the results. What you get. If it is not the same, means there is some issue. But
Yes, sir. In older versions, they don't have arrows.
correct. Yeah. Yeah, then it makes sense. Looks good. So we have port 1, port 2. Change the excitation as off. Electric mode, polarization mode is same 100. Okay. Uh, I don't worry about the other things because there's just air. I don't want to add any diffraction order for air. If it is any silicon substrate in the bottom, then I go ahead and add any higher order diffraction. But right now, I'm not going to add anything else. Okay. Next, any guess what I need to add?
Yes, sir. Boundary conditions, I think we need to apply.
Yeah, correct. Yeah. So, okay, looks good. So, before you do that, if you want, you can change this into wireframe rendering. Wireframe rendering is kind of very helpful to kind of understand, to see through the geometry. Okay, this is the wireframe rendering. Our geometry right now is very simple, but later on, it will become a little bit more complex. So, better is to change to this wireframe rendering so that you get a feel of it. Now we apply a boundary condition on the sides because as this is a mathematical uh, domain, we need to terminate this boundary with a particular boundary condition. So here we use periodic condition. We don't use PEC PMC as of now. You can use PEC PMC also. It's going to be similar result, but as of now use periodic condition, especially because we have used uh, periodic type of ports. Okay, before you apply periodic condition, always good to just click on the go to default view. Otherwise you might be lying something here and here. It's very difficult to apply boundary condition like this. Okay, so best is to click on go to default view and zoom extends, like it's actually any so this is important. Go to default view. Okay, and then click on the left and on the right hand side. Okay, both the x direction. Periodic condition, type of periodicity you change to flocate periodicity, and k vector for flocate periodicity is from periodic port. Okay, we'll wait for a few seconds for you guys to add this. I've added periodic condition 1 and type of periodicity as flocate. Now you might ask, like, why flocate, why not continuity, why not anti-periodicity, and this something new is cyclic symmetry. Okay, so basically if you're applying an electromagnetic plane wave from top to bottom, which is normal, right? Normal means it is perpendicular, right? That doesn't have any angle of inclination. Then you go ahead with continuity boundary condition, you will still get a very good result. But flocate is kind of a very robust boundary condition. So even with angle of incidence as like 60 degrees, 40 degrees, uh, what I mean by angle of inclination is something like this. Okay, so you want to launch the electromagnetic plane wave like this, right? So it is having a particular angle, right? So uh, even with that particular angle, you can actually get the model working. Okay, and usually anti-periodicity we don't use it in optics. So so whether it is continuity of flocate, but flocate will work with both normal as well as angle of incident to be very finite.
So, what do we mean by this flocate periodicity?
Flocate is a person of the name who defined this equation. So what does it mean physically is that if you see this, uh, this- So you have this phase of the electrical field at source, and then you just multiply it with this exponential with the wave vector k, which is defined by this flow kit periodicity, and then just um, add this distance, that is r of dst, that is the distance over here. So what does it mean that electrical field over here and here are the same eventually? Okay, so here and this flow. So here you can see this is a very simplest option. So you just make sure that at each node point on this boundary is equal to the electrical field at the node point over here. The thing that we add with flowkit is the phases. The phase is also same in both the boundaries. Okay, so that is just the new addition that you do with flowkit. Otherwise, most of the other things are the same. Okay, so similar to this, you can add another periodic boundary condition. Either you can duplicate it or you can add once more. If you want to duplicate it, just remove these two boundaries and just add it to the other two boundaries. Okay, periodic 1, periodic 2, just make go to the default view periodic 1 and periodic 2. Okay,
Hello, sir. I have a doubt.
yeah.
Yeah, why didn't we add all the sites in the same periodic condition?
Yeah. Because if you see that it is the electrical field should, for example, your electric field is polarized in x direction, right? For instance,
Yes.
moving like this. Okay, so you cannot apply periodic condition all of them in the same direction, all of them to the same actually. So electrical field cannot be, which is over here, can be same as over here on the right hand side, but it cannot be same on this sides actually.
Okay, but in the case of PEC, we can apply all the boundaries at the
No, no,
same
no,
time.
no, no, no. We cannot apply PEC. You have to apply PEC on these two sides because your
Yeah.
electrical field is polarized in x direction. But you have to apply PMC on here and here.
Okay.
Okay. So this is your name. Sorry.
Jay Krishna.
Jay Krishnan. Yeah. So, but you understand what I'm saying because your
Yeah,
electrical.
yeah, got it. Yeah,
Yeah, yeah.
the direction of the polarization.
The electrical field is polarized in different
Yeah,
direction.
yeah, yeah.
Mm. So periodic condition 1 is similar to PEC condition. Periodic condition 2 is similar to the PMC condition because my polarization is in x direction. Okay. Any more questions? Anyone?
Sir, I have a question. My name is Chetan. Sir,
Mm-hmm.
when initially when we had defined the port and gave periodic there for the port itself, the interpretation of that point was the port is repeating in the space with some periodicity, let us say. But now when you define periodic condition 1 and periodic condition 2, it is the geometry that you are applying the periodic condition. The earlier one was
Correct.
only for the port and not the entire
Boundary,
body
only
as
this
such.
boundary. Correct, correct. Yeah. Earlier I
Okay.
was giving only for this boundary. Now I am giving
Mhm.
to the all the other boundaries because no boundaries should be left alone
Okay.
in this
Okay.
mathematical modeling.
Okay.
Okay.
And in such cases, if we start off with a simulation and let's say it is not converging, then there is an indication that maybe we forgot to give some boundary condition. Maybe that is
Correct.
one
That is a
debugging method.
yeah, it's a ill post problem. Correct.
Okay.
Yeah. Mm, correct. Okay. Any more questions? Anyone?
Excuse me, sir.
Yeah.
Yeah. Yeah. Sorry.
Sir, I'm Jansi.
Mm.
Sir, actually, when you're using two times periodic conditions, will it take one is electric field and another is magnetic field, like
No.
like
Yeah. No. This is internally. It will do whatever. You don't need to worry which one is PEC PMC if you use periodic condition 1 and 2. Just make sure that both are perpendicular. Perpendicular means opposite sides.
okay,
Yeah. So
okay, sir.
it will take care of the. That is just only for understanding that we have been discussing. So you don't need to worry about PEC PMC if you're using
Okay, sir.
periodic conditions. Okay. Yeah. You have one more questions? Anyone?
No, I had it. And Sujay, you were showing the periodic. So this. So now we have in x direction PEC and y direction PMC. And the name actually bugs me a little, because when you say perfect electrical conductor, the medium what we are defining, so our block, air block, has two sides which are perfect electrical conductor, but air, can we say air is a perfect electrical conductor and perfect magnetic
No, no,
conductor?
no. So don't worry about that as air. Means what we are, because this is a modeling geometry, right? So we need to terminate it somewhere, and PEC,
Yes.
PMC are all terminating boundary condition. What does you can if you want to be you can just one way to look into is that perfect electric conductor. What does it do is that if the
It
electrical
short
field is
circuits.
yeah, it short circuit. So if either another way to say is that if electric field are coming normal to this PEC, it will just make it zero. So the n cross E is equal to zero, right? So one way to
Mhm.
look into it is that, right?
But if we want to like have a real life
So it's
simulation.
real life, right? For example, what I'm saying is that it's an infinite geometry, right? So the infinite geometry means there's no reflection. What I'm saying that whatever you're giving me, I'm just accepting it. Assume a room,
Okay.
right? One way of looking into a room which is infinite uh,
Hmm.
dimensions in means infinite in width and breadth would be something like if I throw a ball, it doesn't come back, right? So
Hmm.
what I'm saying, I'm just
Okay.
whatever I'm throwing to this walls, it's going to absorb. Nothing is going to
Hmm.
reflect,
Understood.
right?
But
So
there
this
is
is the
no boundary condition where it translates through the boundary and does not reflect. There is no such thing. There is no such
that's the
thing.
PML is there. So there's
Okay.
a volumetric boundary condition. Now we don't want to play with volumes. We are just like
Okay.
if you can actually deal with boundaries is always good because volume will add more mesh elements, right?
Hmm.
So if you can do with boundaries, it's always good.
Okay.
Okay, but yeah, you as you said that there are, so what I'm wall, so PMLs perfectly matched layers are like
Hmm.
walls. So there are
Hmm.
thick walls which if you absorb it will absorb the electric fields. It will take some time to absorb, but it will eventually absorb the electrical
Okay.
field in some time.
Mhm. Okay.
Okay,
Thanks.
that's good. Yeah. Okay, looks good. So let us take a break of 20 25 minutes and again join back at 5 o'clock IST to take this forward, this model forward, and then we can also have a one-on-one discussion after this. Okay, thank you. If you have any more questions, please don't hesitate to write down in the chat box. We'll again follow. Thank you.
Thank you. Will this meeting continue or we get out?
No, no, you can stay in the same meeting. Yeah,
Okay.
we'll take a break for
Okay.
20
Understood.
25 minutes and then again get back to our business.
Okay. Thanks.
Hello and welcome back. Uh, Let me know if you have any questions or query, or we'll start the session. I'll wait for a minute for people to join back.
Sir, how we can decide the periodic one and periodic two is going for the T and TM polarization?
Okay, just hold on. So can you please repeat your question? Sorry.
Sir, here we are taking the two periodic boundary conditions, that is periodic one and periodic two. So, and both have a flocate mode. So why we are not taking a single boundary conditions? If we are taking the two boundary condition, that means we are going for the T and TM polarization. So which boundary condition is going for the T polarization, which boundary for the TM? Because we don't find any such kind of electric and magnetic field orientation in this setting of the periodic condition.
Okay, so basically means if you are working with periodic conditions, you don't need to worry about the polarization. Okay. The reason why we discussed about PEC and PMC was for something else. This was symmetry boundary condition. Okay. If you want to divide the geometry into a quarter part, and then so either you launch T mode, TM mode from the top, you apply this periodic condition, but that those has to be just in opposite, diagonally opposite directions. And if you are making periodic, you don't need to worry about anything else. You can launch any mode of propagation, either it is T mode, TM mode, S plane, P plane polarization that you mean. Right? So you can launch any mode. But this is a kind of configuration that COMSOL have introduced. So based upon that requirement, this periodic condition should be mentioned in the opposite direction.
Yes, so basically I'm using the like in the microwave studio CST and
Hmm.
Ansoft HFSS. We are just like mentioning there flocate boundary conditions, and we have defined which boundary condition like a master slave, the direction of the electric and
Okay.
magnetic.
Yeah. So it's same as master slave. You can see source and destination here. The source is the master
Okay.
and the destination is the slave. So this is the source. This is the slave.
Okay.
Yeah. It's the
And
same
that's
thing
why we are
actually.
taking a combine of two phases.
Correct. Exactly. So it's just copy pasting. If you see this continuity, is just destination is equal to source, like master is equal to slave. So just copy and pasting without the information on the phase. Flocate is just adding the phase information.
Yes. Definitely it is going for the periodic end, so it will
Yeah.
be added.
So it's just same as that what you were saying about master slave. Yeah, correct.
Okay.
Okay, that's good. So the next thing is the mesh. So here, if you just click on the mesh and click on build all, I hope you guys have back. Okay, I'll just start the session. If you have any question, just let me know. So this is the mesh. But one thing that we have selected here is physics control mesh. If you see this physics control mesh, we have enabled it. It's very important to use physics control mesh because our worry about meshing it correctly goes away. Okay, so here you can see that based on the wavelength that is mentioned in the wavelength domain. Now let us see what wavelength have been mentioned in wavelength domain. It's mentioned on 1 micrometer, but that's not what we require, right? So we require LDA naught. So the LDA naught is uh, LDA naught. So this is what we need to mention over here, LDA naught, right? And then again go to mesh and click on build mesh. So here you can see there are slight changes in the geometry. Okay, so I think Kavita has a question about user control mesh. So I will come about user control mesh in some time. Okay.
Udam, my name is Faraz. I'm trying to click build all, and it pops up some error, failed to set mesh size automatically.
This build all.
Yeah.
Okay. So did you go into wavelength domain and see it is LDA naught, the same thing
Yes.
that you have mentioned in?
Yes. Yes.
Okay.
Yes. Yeah.
So next thing is to go into geometry and just make sure that the length unit is in nanometers.
Yes, it's in nanometers. I checked it.
So once you click on build all, what error is it showing?
It's showing failed to set mesh size automatically.
Yeah. Okay. Perhaps you can share your screen. I can just look into it.
Yes, I will share my screen. Can you see my screen?
Perhaps it's just loading.
Can you see
Okay.
the error? Can
This air domain, can you assign the air material is showing some kind of exclamatory yellow color? Can you apply air? So is the domain is not selected. Can you apply the domain here? Air. It's blank, right? Selection is blank. Just left click the domain on the right hand side. Right hand side geometry. The rectangular thing is there on the right hand side. Just left click on that. Just left click on that. Left click. Yeah. So now it shows on that exclamatory mark is now gone, right?
Okay, okay, okay.
Yeah. So now click
Yeah,
on
yeah,
mesh. Oh,
yeah.
good.
Thanks.
That's good. So let me share my screen again. Yeah, that's good. So basically, we have the mesh. Kavita was asking about the user control mesh. Now, yeah, you can also go ahead with user control mesh, but if you're using physics control, this wavelength domain or frequency domain, the best way is to go ahead with physics control mesh because um, yeah, because I need to show you why. So now, for example, I this is my modeling domain. Okay, but there's some noise coming. Anyone has a question, or you can mute yourself. Yeah. Okay, that's good. So basically, if this is a modeling domain, and you want to model, you want to launch a electromagnetic plane wave like this over here, and to right hand side over here. So basically, you want to model like a plane wave propagation like this. This is kind of different as what I've drawn here, but this is what is the wavelength. So if you see, this is that one wavelength starts from here and then it ends over here. So basically, the mesh requirement is it requires at least second order mesh elements. Now, second order is again what we discussed in the morning. Sorry, not morning, in the first session. So it's a linear elements. It requires at least second order, 5 second order mesh elements per wavelength. So it could be something like this. Okay, sorry. Okay, so you can see this is my first, this is my second, this is my third, this is my fourth, this is my fifth, this is my sixth. So at least 5 second order elements. So this each one is a second order element. Okay. So in single wavelength, this is a single wavelength as you know already. Okay. Single wavelength, it requires at least 5 second order elements Right now it's around 6, right? This is automatically controlled by the physics control mesh, so you don't need to worry about it. But if you use physics user control mesh, then you have to make sure that you write that equation, that is lambda by 5 divided by n means the refractive index of the domain. So right now is air, so it's just lambda by 5. But if it is a higher refractive index, a real part, then it actually increases accordingly. Okay, so I hope I answer your question, Kavita. Okay, one more question by Kavita I was is uh, about this degree of freedom. Okay, so here you can see the each, so this is known as node point. Okay, each node over here. Now what happens is that uh, this each node point, so what does COMSOL do? COMSOL solves at these node points. Okay, what does it solve? Can anyone tell me? So what does COMSOL do? It starts from here, okay, and it's actually keeps on solving. So what does it solve for? Does anyone know?
Maxwell's equations.
Sorry.
Maxwell's equations.
But what variable does it solve for in
Electric field.
Maxwell's? What is the first thing that it solved for? Any guess?
Electric field component.
Yeah, correct. Yeah. So that electric field component, that is also known as a dependent variable. So if you go to electromagnetic wave frequency
Electric
domain
field.
and you go to dependent variable, yeah,
Electric
exactly,
field.
electric field, correct. Yeah, correct.
Yeah,
Electric
electric.
field. Can you hear me? Yes. Yes, yes. So here you can go to electromagnetic wave frequency domain, the dependent variable. This electric field also is not just a single variable, it has three components, right? So each node, this is each node actually solves for three variables. So EX, EY, and EZ. Okay. So now if I have a single point over here, so just single point, I'm just trying to solve for a single point, and there are 3 degrees of freedom. Okay, now based upon the number of mesh elements or mesh node points, you can see that you can multiply the mesh node points with the number of variables that we are solving for. Okay, so that is the degree of freedom, total number of degree of freedom, number of node points into the number of degree of freedom. So the total, sorry, dependent variables. So that is the degree of freedom eventually. So higher the number of degree of freedom, higher the time that your modeling, your model will take to compute. Best practice is around, if you have a system of 16 GB, your number of degree of freedom should be less than 0.5 million. Then you can be happy and you can converge your model very easily. But if it is going from more than 0.5 million, then it's very difficult for a 16 GB laptop to, even 32 GB is sometimes difficult. Okay, so best practice is to keep it less than 0.5 million. Okay, I hope I answered your question, Kavita. Sorry. So next thing is the mesh, and what I want to show you with the mesh now is that how it is wavelength dependent, because it's a physics control mesh, right? So now if I go to my parameter, and instead of 600 I use 300 nanometers, like, which is a very difficult number to work with, especially in optics, and then I click on build all. So here, did you see the difference? Now the mesh is kind of significantly um, increase the node points. Here you can see that on the number of domain elements, it has increased by almost 10 times. It was around 1387 earlier when I was operating around 600 nanometers. Now I am operating at around 300 nanometers. And on degree of number of domains have been increased by almost 10 times. Okay, boundary elements have increased by almost like, how many? Oh my god, that is like 8 times. This is also twice the number. Okay, so so the mesh is actually dependent upon the operating wavelength. Okay, so now if you're using physics control mesh and you're running a parametric sweep of wavelength. Okay, so in that case you can see that your wavelength, your mesh will change every time the wavelength is changing. That automatically will happen and you don't have to worry about it. Any questions, any doubt? Okay, so looks good. So that's it. Just go to the study and then click on compute, and then let us see. You can see your degree of freedom as well. It's showing around 10,000 degree of freedom. So don't run the model with 300 nanometer operating wavelength. Run with around 600 nanometers.
Hello, sir. I'm
Yeah,
getting an error. Yeah, it
yeah.
is
What is the
saying
error?
fail to set up. It is saying fail to set up physics controlled mesh and
Fail,
fail to set
fail to
mesh
set up.
size
Okay.
automatically.
Yeah. Can you share your screen?
Yeah, 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 sir.
Anyone getting the results?
So this is
Huh,
Ayushi. Can I share my
sure, sir.
screen?
Few seconds.
It's
Yeah. You're also facing issue.
no. But it's like, I mean, aesthetically, it looks little different. Maybe it's because of the version. I show you.
Okay. I think Padampriya
Oh,
was
okay,
sharing
okay.
her screen.
Sure.
After this, you
Yeah,
can
no
share.
worries.
Okay, looks good. Uh-huh. Yeah. So fail to set up physics control mesh, fail to mesh size automatically. It's the same problem that Faraz was facing. In the air, you need
Yeah,
to
so
select
I
the
have
domain.
did. Can you
Air, there
able
is an
to see my
exclamatory
screen?
mark, right? Yeah. Yes, Padampriya, I can see your screen. The air, you need to select the domain. Just left click the domain on the right hand side. No. On the right hand side,
1 second, sir.
that right
Where?
hand side geometry.
Okay.
No. Right hand side
Oh,
towards geometry GUI. The right hand side, the rectangle. Just click on the rectangle
yeah.
block. Left click on the rectangular block in the GUI.
You need to
Uh,
move the cursor in the right hand side. Sir is telling right hand side. You are
right.
keeping left,
Yeah.
right.
Just click on that. It was
Yeah.
a red color, right? It should be.
Okay, sorry.
But you first go into the air. Uh,
I'm in air actually.
Now, as
Huh. Here I could see the geometric
yeah,
entity
yeah. So
selection
move your
domain. This
cursor
is
to
what
the
I
right hand
could
side.
see.
On the just move it to the block.
Okay. Okay.
Yeah, just left click on this. Left click.
Okay.
Yeah, yeah. Then I think the periodic condition is also not completely full. That's why exclamatory mark is coming with periodic condition 1.
Okay. Fine, sir. Actually, I could left click. I could do that, but I'm not getting any options.
No, you are already selected it, no? But now it is you have deselected it again. Just left click again. Yeah, but that's it.
Okay.
Oh no, it's gone again. Just left click, so this one should come on the domain selection.
Is it coming now?
Means, I don't know, you should be a better position to see that. Yeah, now it's good, right? So one is coming in this selection, right? So don't change it now.
Yes.
Okay, now you can go to
Okay. Fine.
periodic condition 1. Oh, but it's again gone. Okay, yeah, just keep it and then see the periodic condition 1. Okay,
Okay.
and then again change it. Okay, see
No,
the
if I
periodic
remove
condition
my
1.
cursor, it is
Mhm.
going.
Oh, is it so? It
One.
didn't go now.
Yeah. Okay,
Okay,
fine. Now I'm going to periodic condition.
yeah, then you select two diagonally opposite boundaries. Okay. Similar with periodic 2. What you do it with periodic 2?
Periodic 2, I just duplicate the periodic condition 1 and I selected
But
the
you
other
have not
side.
selected boundaries, right? You have to select the boundaries. Diagonally opposite boundaries. Not all boundaries, just diagonally opposite. I will share my screen, just see what I am doing, okay?
Okay,
Wait.
fine. Yeah. Should I stop sharing my screen?
Yeah.
Okay.
So you can see my screen, hopefully. Okay, so you can see this periodic condition 1. Okay, so I have done diagonally opposite. You can just enable the wireframe rendering and diagonally opposite boundaries I have selected. Okay, similarly periodic 2, diagonally opposite other two boundaries that I have selected. Okay, and then you can click on
Okay,
study
one
and
second. Yeah.
yeah, you can try it out till the time I can try to resolve.
Ah, okay,
Uh,
sure, sir.
Ayushi, you
Thank you.
can share your screen. Yeah, one more thing
Okay,
actually
sir.
before Ayushi actually you share the screen, I would like to show you because the result what you are seeing right now is like a more like a noise. Okay, so the what I want you to go is go to electrical field multi-slice, and instead of normalized electrical field, you plot EX field, that is the X polarized electrical field, and then click on plot. Okay, so here you can actually see the electromagnetic wave propagation, right? So please try to plot this multi-slice plot in the electrical field multi-slice. Try to compute EWFD.EX. Okay, that is X component of the electrical field. Okay, so yeah, Ayushi, now you can share your screen.
I think without even putting this EX, I was getting this only, which was different from what you were showing. I will just
Okay.
quickly share.
hmm Yeah, that's because of version difference, I guess. But now, if you put EX, is it the same thing that we are getting?
Okay, I think. Yeah.
You can share your screen. You can
So
click
can
on
you?
present now.
Yeah. So can you see my screen now?
Yes, I can.
Yeah.
Yeah, it looks
So
good. Yeah, it's for
yeah.
10 power
So
8. Yeah.
even before doing that EX thing that you did now,
hmm
I think I got this, which was different than
Yeah.
what you
Can you
showed
go into that
earlier.
electrical field inside electrical field and what is the variable being used now?
Here.
Just double click on this.
Yeah. I clicked it now.
No, just open that electrical field EWFD on the left hand side. No, on the left hand side. Uh,
This
go below. No.
here.
The third. Just left click on that corner. Uh,
Oh, this one.
Corner
Multi-slice.
triangle. Correct. Yeah, multi slice. In that multi slice, what are you plotting? Okay, norm E. Okay. Even with norm E, you are able to see this. But what I want you to do instead of norm E, you write
Yeah.
EX, capital E, small x.
Or I think the wavelength
Here.
is 1 micrometer.
Okay.
The
No,
Here.
but
wavelength that she is getting,
wavelength
no, the wavelength that
you
she is
can,
getting is around 1 micrometer. I think so.
yeah, you can check the wavelength as well. Just click on plot first. Plot.
Now I've clicked. I've written EX. Now what should I
Now
do?
click on plot.
Plot.
Just top,
Where is it?
top. Yeah,
Oh, here.
yeah, correct.
Yeah.
Yeah, so this is the actual this thing. So
Okay.
yeah, so you can also go to the wavelength domain
Wavelength.
in study one wavelength domain.
Yeah. Yeah.
Yeah. Hmm. You use what wavelength have you mentioned here?
Yeah.
1 micrometer. Yeah, so you need to change here to LDA not the same that you mentioned in the
Yeah. I
parameters.
think I zero. So I think I
Hmm.
missed this part. So now what do I do?
Compute again.
Okay. Compute.
Yeah, in the top below wavelength domain.
Sorry. Uh,
Yeah, no, in the middle, in the top setting
um.
middle. No, you go in the middle of this settings pane top.
Oh, here.
Yeah.
Do I do it? Okay.
So you can
Okay.
also understand that if it is around 2000 nanometers, so it will take around 600 is the one. So around 3 peaks you'll be able to see, right? Almost 3.5 peaks because it's around 2000. So you can see there are 3 red peaks and half of the red peak. You understand, right?
Oh,
Because the
yeah.
three wavelengths is
One,
kind of
two, three,
visualized.
and this half.
hmm If you make
Okay.
around 1800 nanometers, then only perfectly 3 waves you will see at the same time. Okay,
Okay. Okay.
looks good. Anyone else
Um,
having facing any
the
problem or getting results? Yeah.
Yeah, Uttam, I'm facing an issue. I would like to share my screen.
Yeah.
Could you see my screen?
Yeah. Perhaps it's loading.
Yeah. Um, so when I'm clicking on compute, here it pops up this error. The periodic boundary condition must be continuous. I think I have done. I think something is missing in port two.
Yeah. Can you go to periodic condition one? Sorry.
Okay.
What was the error you said?
Yeah, yeah. I will show it to you. So when I click compute, it says the periodic boundary condition must be continuous. Feature port two.
Somehow I cannot see the error. I can see only the COMSOL. Perhaps you have shared only the COMSOL. I don't know.
No,
Anyway, I trust you.
uh,
Yeah, I cannot see the error, but yeah, you can go to the port one. I will just go through.
yeah. Port one.
Okay, port one, periodic condition. Can you go down in the settings pane? Okay, this looks good. Go to port two. Yeah, go down. Periodic. Oh, this no, no, no. So you see there are you have selected both the boundaries.
Okay.
So port one only single boundary, port two only single boundary.
So I
Okay.
have to I have to delete fourth.
Mm-hmm. Yeah, yeah. So if port,
Yes.
no, you can delete anyone. So just make sure that
Okay.
they are not same.
Okay. Port one is top one and okay. Port one is okay.
If you do that, then both of them goes away.
Yeah,
But
both of them goes away. Yeah.
yeah,
How?
anyway, you can manually select by your clicking your mouse button. Just
Yeah.
rotate it. So yeah,
Uh,
correct, correct. Yeah, that's correct. Yeah,
but again,
just
it's still not. Yeah, like
left click.
this.
Yeah, left click. Yeah, just go to port one again and see if it's not the same number four. It's the same four. So you need to choose the other side actually.
Okay. Yeah. Here I have to delete it again, and this one.
Yeah, this looks
Yeah.
good. Yeah, this looks good. But this wavelength have you put in this wavelength domain? LDA not in wavelength domain.
Yeah, I have already put it. Yeah, I have
Okay,
already.
fine. Now you can change this in multi. You open the electric field plot and then change in the multi slice parameter that you are plotting, and you go to the reset 3D view.
Sorry. How to go to
Right.
the receptacle?
Um, in the graphics, can you see the graphics pane written graphics? It's the fifth button from the top left side. In the graphics, below
Yeah.
graphics, left from the left. You came from the right, right? Correct. Yeah, correct. Left click on that. Not on the arrow, just on the left. That one. Left click. Good. Now you go to electric field. Open the electric field in the plot setting results section. Open it. Yeah, double click that or double open it and go to multi slice. And then instead of norm E, you write EX.
Okay, and then
Non plot again.
go to study
Plot
and
again.
you.
No, 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 no. You don't need to do again.
Okay, plot. Okay,
Plot.
okay, okay.
Yeah. Okay, perfect. Looks good. Okay. Okay, so that looks good. Meanwhile, there are a few more questions. How you calculate the peaks that should be 3.5? Which peaks are you talking about? The peak of the electrical field? I don't know. Someone is honking. Uh, Krishna, can you mute yourself? Or anyone else also? Ayushi, you have a question? Otherwise, you can mute yourself as well.
Yeah, sorry. So I think I have the same question as hers. Like you told that for zero point 0.6 micron, which is 600 nanometer, we have three complete red peaks and one half red. which is 3.5, like 3 red and 1/2 red. So
Hmm.
I cannot actually understand the graphics of this diagram, like probably. So how do we see this graphics basically? Like you told that if it is 800 nanometer, we'll have four complete red, you
No,
know,
if it is 800 nanometers, means you will have only two and a half.
2.5. Okay.
If, for
So
example, now
what is
if
the meaning of this? Like,
yeah,
how
yeah,
do
I
we
will show you.
understand?
Yeah, yeah, that's interesting because that's what. So now, for example, if I put 2000, now can you tell me how many red would be there? Any guesses? Any intuition? Anyone? I have put 2000 wavelength. Wavelength is operating wavelength 2000, and my geometry length is around 2000. So how many red and blue spots would be there?
1,500.
Thousand and half. Sorry, I didn't get you. Who is it? Sujay?
For
Faraz.
us.
Yeah, hi. Uh, thousand and half means how many peaks, red peaks would be there if I put operating wavelength as 2000 in a waveguide which is having a length of 2000.
A single one, probably a single,
Sorry,
probably a single peak.
single peak. Yeah, correct. So let us see that. So here actually, um, so if you see. It is actually a single peak but it's discontinuous. Okay, so if you see this blue peak, it is a single peak, right? So this is single. So what is happening, if I just show you once over here, so I have a domain which is around 2000 nanometer long. Okay, and what I'm saying, my operating wavelength is also 2000. Okay, so what does it mean is that I will be having a single wavelength, so means something like this it would be there. This is how the electromagnetic wave is going to propagate. When I mention LDA naught is lambda is equal to 2000 nanometer. You understand, everyone? But what you see right now in your screen is the phase which is shifted. Phase is shifted by 90 degrees. So it's actually is something like this. It is plotting, but it's still 2000 nanometers. It's still the single wavelength. Are you able to get me? Any?
So,
Yeah.
Uttam, you mentioned about operating wavelength is 2000 nanometer, right?
Yeah, yeah, correct.
And you also mentioned another value which is also 2000 nanometer.
It's the
What's that?
length. It's the length of the waveguide.
Okay, and we are getting one is because you are dividing it. You are dividing it,
No,
right?
no, it's just a wavelength. So wavelength means what is from between the two peaks. What is the distance between two peaks? So if you define what is a wavelength, wavelength is nothing but the distance between the two peaks. In
Okay,
this case,
yeah.
it's matching. It's the same with the length of this waveguide. Okay, so that's why you're seeing this kind of. This is actually the same thing what you see over here. But here it is just the two peaks. The distance between the two peaks is around 2000 nanometer. That's the definition of the wavelength, right? Spatial distance.
Yeah, but this one we are getting you showed you change the value to 2000 and then we see that there is only one peak. So how this
No,
calculate
no.
which
This is one peak means here actually is what I'm saying. It's actually a one peak only, but it is phase
okay.
shifted by 90 degrees. Okay,
Okay.
so if you see, this is a sine wave. It's kind of a
Okay,
cos
okay.
wave.
Yeah, yeah,
Understand?
I got it. I got it. Yeah,
Yeah,
I got it. I got it. But in the example, you put 2000 nanometers, and
yeah.
the peak we are getting is only one peak. And before that, when we put
Uh,
600 nanometers, we were getting 3.5 peaks. So
yeah.
what is the mathematical calculation behind this? Like we are getting 3.5 peaks when we put 600 nanometers.
Mhm.
So this is what
So
I
yeah,
want
yeah.
to
So
understand.
you will get to know once you do the animation. You will get to know.
Okay.
For example,
Okay.
here do we get the? Can we? This is a phase. So I will change. I will reshift the phase from this to 90 degrees. Okay. So I'll shoot an angle. So now if I plot it, it's this one. Can you see this plot? It's a this is what I draw, right? So if you compare this with this guy over here, right, the same thing as you can see over here, single wavelength.
Okay.
You see, if I draw a line in the center, you will see the same thing what you see over here. Okay. Now if you make this as 600 nanometers, okay, and then again plot, then you will see that this length is six to total around, how many would be there? So 600. So if this is 1000, this is 500, this is 500, so 600. So it would be single wavelength would be ending around 600. Okay, this would be the 600 plot.
Okay,
Then
so
again
it's
it will
showing.
go.
Okay, so
Sorry.
it's showing the single wavelength, right?
This is second. It will die down over here.
Second.
Second wavelength. Then
Okay.
around 1800 it will die down. Sorry, this is
Mm.
600 nanometers. Okay, this is 1200 nanometers. It die down again. Then next is around 1800 nanometers. So it will die down around 1800 nanometers.
And in this example, which you are elaborating, what 200 and 2000 nanometer is, what is the
The
operating
length.
wavelength? Is the
No, no,
length?
no.
Okay, is
Yeah,
the
in
length?
this case, it was operating wavelength and the length was same because I wanted to show
Yeah.
you that it is
Yes.
just a single thing.
Yes.
Right now, if you can show, you see this same thing what I have drawn over here. You see,
Yeah.
it's
Yeah.
it's our high 1, 2, 3, and then here
Yeah.
again one small peak would be coming. So here
Yeah.
is a high, 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 and then one more peak is coming. Just starting
And this in this example, the operating wavelength is
600 nanometers.
600 nanometers. Okay, and
Yeah,
the length is 2000 nanometer, right?
2000. So now,
Perfect.
yeah, anyone can guess about if I put 1000, then how many peaks will I get? Means how many wavelengths? How many
One and a
wave?
half
Two,
peaks,
sir. Two.
one and a half
Two,
peaks,
right?
Two,
Yeah,
two,
two peaks you
two,
will
exactly.
get
Yeah,
two.
two.
correct. So here you get two of them, right?
Yeah.
So, so that's why it's very
Um,
important to visualize what we actually, because we always say that because electromagnetic wave we cannot see, right? So that's why it is taking us time to understand how it is going. But that's how COMSOL is very helpful to visualize the electrical fields. So once we have that in our hand, then it's good. But by default, it would be zero. So just makes the result would look something like this. So even though it is actually two only, because this is half and this is half, the center is the full one. So actually, it's just two peaks. Okay.
hello, Professor.
Yeah.
I'm not getting the results that you are getting on your screen.
Yeah. Can you
Um,
please share your
no-
screen? I can just
yeah,
look into it.
I can just share my screen.
How about other guys? Are you guys getting? Are you guys trying? Or
Yes, sir.
okay, great.
Professor, can you see my screen?
Yes, I can see your
Yeah.
screen.
So,
Oh my God, what is this? Our ad? There are so many things, but yeah, this one only. Okay.
yeah.
Yeah, so you need to go to multi-slice.
Uh-huh.
Yeah, change from norm E to
Oh, okay.
EX. Don't you go there and go change just just select this norm E by your mouse and just remove that and just write capital EX.
No. Oh, okay, okay, okay.
Capital
Hello,
EX.
sir.
Yes, Sabita, you have a question? A small X.
Oh, yeah,
Yeah.
yeah. Got it, got it. Okay, 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 okay. Thank you.
Oh wow, you how much wavelength did you use?
I I gave 300 for
Oh
my
wow, that's what. Yeah, yeah,
yeah.
yeah.
That's right.
Good, good, good. So yeah, interesting to see would be your message. If you go to the message box, interesting to see would be your number of degree of freedom. So you solve for 87,000, right? It's
87.
almost like 1 lakh or like 0.1 million. Okay,
Oh
so
yeah.
you can go ahead till like 0.5 million, like without having
Okay.
some problem. So it just take 5 seconds right now.
Uh-huh.
You just
Yeah.
send 0.01 million, right? Yeah, correct. Yes,
Yeah.
Sabita, you had a question. Yeah. Anyone has question?
So
Okay,
this
can
is
you
Jay
please share?
Krishnan. I actually have a question.
Yeah.
So since we have selected our polarization along the x-axis,
Mm-hmm.
for the norm E itself, we should get some results, right?
Yeah, so let me just write the definition of norm E.
It's
So this is
normalized
little bit
electric field, right?
confusing to work with norm E. So norm E is, can you see my screen, right? So norm E is nothing but square root of
So
E x square plus E y square
Achha.
plus E z square. Okay. So what is happening is that because this is a square term of ex field, right? So if you see this, so it will also, or you can, negative values are becoming positive. Okay, and it's almost becoming the same. Okay, very high values. So if you see that little bit fluctuations would be there. If you see over here, if I plot this norm E,
Okay.
it would be, so here you can see the fluctuation, right? 10 power 7 to minus 10 power 7, right? You can also enable this show maximum minima. So you see highest is like 10 power 8, and
yeah, which so
yeah,
which means we are also getting the contributions from EY and EZ components.
no, no, ey
Yeah.
ez is almost zero.
What do you
Almost
want?
zero, but it is not zero in this case, right?
Yeah, it is almost zero,
Why
correct.
is
But
it
this
happening like this? So is the
comparing
whole part
it will be very much minimal. So here you can see, if you write ex, you have like 10 power 7, positive 10 power 7, and negative is minus 10 power 7. Okay, now if you put
Go,
ey,
go in the plane.
you will get, it's like yeah, ey component would be there because of the magnetic field. It is still there, but ez component would be
that is
almost
also there,
zero.
sir. Actually, it is also kind of there.
Oh, it's still there. Okay.
Yeah, that's
So
why.
but
Holy
yeah,
cow.
yeah.
14 hours. 14 hours.
So this one
So, yeah,
getting a
it's
lot of noise.
wow.
Who is asking the
No,
question? I have no.
It's me, Jay Krishnan,
Oh,
sir.
So Arvind, can you please mute your mic? Yeah. Sorry, Jai Krishnan. So what? So if you plot this norm E, what you see is that first thing is that it is a positive value. Okay, all of them. There are no fluctuations. Okay, and all of them are kind of very high values. So it's kind of almost constant, right? So what was the question? Sorry, I couldn't get it.
So the thing is, like, since the polarization is along the x-axis only,
Okay.
so why are we getting the magnetic field components in the y-axis, also in the z-axis? That was my doubt.
If we have
Because
the
of that only, we
electrical
are getting the
field,
noise, right?
no, this way. 10 power 5. Usually the magnetic field would be there in y direction. So
Yes.
Hy would be almost the similar value.
Yes.
So it's 5. So Hx should be almost like
Blue. It
very
will be
less. But
completely. It should be completely blue.
no, no, means here, what, yeah, I understand what you're saying. What you're getting is like if you compare it, the magnitude is like 10 power 4 times lower.
Okay.
Okay, Ex is kind of 10 power 7, Ey is 10 power 6. 10 power 6, not 10 times lower, but still it's significant. So your question is why we should not getting 0? Is it to do with periodic conditions?
Yeah, I think.
Yeah,
Is it there anything like that, sir?
I don't know. It's the way it solves Maxwell's equation, and then it's all. But one way to check whether the modeling domain is results are correct or not is always to check your S parameters. Okay, S parameters. If you check, I will just come to the definition of S parameters. But to right click on the derived values, global evaluation.
Okay.
You just search here for S21. Okay, and as you know, in optics we search for absolute values of S21 square, which is the transmittance. Okay, so because this is the air domain. Okay, air domain transmittance would be how much? Anyone?
One. It will be one.
One, right? Yeah. So here you see that it's almost one. So that is a way to one of the way to check that what we are
Just
doing
one.
is actually correct. So a reflection, because there is no um, reflecting geometries. So if you see, the reflection would be almost like zero. So it's almost like zero. 10 power minus 7. Okay.
So if you're getting a noise like this, we can check in this way.
Yeah, yeah. So you can see that
Yeah.
this value should be almost like one and should be
Mhm.
almost like zero, right?
Okay.
One more way to check is you just go to the multi-slice, and better for visualization purpose also is go to the animation view and
Okay.
click on player, okay, and then you change this as phase dependent, that is dynamic data extension. Change the sequence type as dynamic data extension, that is phase dependent animation. And once you click that and make a repeat forever, and then click. So once you do that, you will see the propagation, how the electrical field is being propagated. Okay, this is also very important to see when whatever model you're doing, you always start with air domain. Okay, and with air domain, you are able to see that your electromagnetic wave is propagating in a particular direction. Unless until you do this animation, you will not be able to see in which direction it is propagating.
Yeah.
No, actually, I have done this, but I am not seeing this animation.
Yeah. So have you used dynamic data extension?
Yes, I have used dynamic data extension and full harmonic and selected forever, and then I clicked on the show frame.
Yeah. Which
Uh,
expression are you evaluating?
I am evaluating EX.
Okay. And did you click on play?
Oh, wait a minute. Yeah, now it's running. Yeah, now
Oh,
it's running.
cool.
Thank you.
Yeah.
Hello, sir.
Yeah.
Sir, I am facing an internet issue since 4 o'clock, so I missed a major part of this
No
training.
problem. We are recording this session, so anyway, you can. I will be sharing once the video processing is done by the Gmeet app. I will share it
Is
in.
it possible to share it by tonight, sir, so that
Yeah, yeah. I
tomorrow
will share by tonight. Yeah, yeah. I
okay,
will do that.
sir, where will you you will share in the G drive
Email.
email?
Email. Yeah. It will be a type of a Gmail, G drive only because that's only is allowed through
Okay, sir, please
Gmeet.
do it, sir.
Yes, we'll do that.
Okay,
Thank
thanks,
you.
thank you.
Hmm.
Hello,
Yeah.
sir.
Yeah. Hi, Pratik.
Excuse me.
Hi, Jansi. So, Pratik, yeah, you
Yeah,
can.
sir. I have two questions. One question is you have used the port one. So with
Okay.
instead of port, can you use the scattering boundary condition?
Yeah, I will talk about it tomorrow. That is the one way. So port was one of the way to launch your electromagnetic plane wave. Another is scattering boundary condition, which is even more versatile. So we'll talk about
Yeah, sorry to interrupt, sir. We are
yes.
getting the same results. I have used a scattering boundary condition, so we got
Mhm.
the same results actually.
Same results. Miss, which
Like
result you're
the
talking about?
results are
EX and
matched.
EY.
Like no,
Okay,
you
okay,
yeah, the same thing. Like you did it with
great.
port, I did it with
Uh,
the scattering
okay,
boundary condition. Both are same.
yeah, same only. Yeah,
Okay.
that's great.
Yeah,
Yeah.
actually, sir, in some cases the result were same. But my question is when we use the port and when we use the
Yeah, yeah.
yeah.
So basically, the scattering formulation we use when we want to evaluate or quantify the scattering. Okay.
Okay.
So with using port condition, you can evaluate S parameters. Okay. S
Okay.
parameters means, for example, it's a two-port network. For example, let me show you here. So this is a dielectric domain. Okay. It, however, it actually works as a two-port network system. That is, this is my port one, this is my port two. Now, what does it mean is that if I am giving my input over here, okay, and I'm taking my output
Output.
from over here. Now, the scattering parameter is defined by SAB. Okay.
Mm-hmm.
Now, SAB means this is my output.
Output by input, I think.
Yeah, and this B is my input. Okay. So now if I mention it is S21, it means the amount of energy that is thrown outwards.
Transmitted through the
Transmitted,
yeah,
exactly. Yeah,
by
transmitted.
the
Yeah,
incident.
that means output is port number two, input when the input is one. Okay. Now if I mention S11, S11 means output
Reflection.
is one and my input is also one. It means how much is the reflection.
Reflected. Yeah.
Okay. So port condition will help you to get these parameters. So it's eventually it's a S matrix. Okay, you have S11, you have S12, you have S21, and you have S22. Right. So all the parameters matrix you will get this as matrix.
Okay.
Usually you actually work with this one for reflectance and this one for transmittance. So you
Transmission.
use this absolute value of this one, and square of it will give you transmittance. Okay, and then you use square root of a reflection would be like absolute of this as 1 the whole square.
Uh, uh, I got it. Actually,
Yeah,
so sir, actually, to get the S parameter, we will use the port one.
port condition, that is the
Uh,
only way to create well, you can even with scattering
con-
formulation you can actually calculate the s parameters, but
mhm.
you have to integrate how much the power flowing in that boundary, so
Yeah.
those are a little bit complex, but you can still get that because s parameter is nothing but the ratio of power, right? So
Okay.
power which is thrown out in second divided by power which is thrown in the one,
Uh,
right? So eventually it's like ratio of power, so you can also
Sir, I have one more question. In the maze thing, you have used the normal one, but there are another one thing extra fine, finer.
yeah, you can go with
So,
normal, that is because normal actually all of them actually will actually have the physics control mesh.
mhm.
So that is the minimum criteria of lambda by 5 has been satisfied by all of them if you use this physics control mesh. This is the
Yeah, yeah,
criteria,
they have
right?
same
That
here.
is being this criteria is um, uh, ticked marked, or this is enabled by this physics control mesh. So unless this is ticked marked, actually you are safe.
Okay. So, is there any means when we use the normal one or extra fine or finer? Is there any?
Yeah, basically, I will come to that when we talk about this optical fibers.
Hmm.
Um, and specifically when we are dealing with very small structures with high aspect ratios, and for example this big geometry is there, right? Now
Hmm.
you have another geometry which is like very very small, a gold nanoparticle which is like 10 nanometers, right? So there's a huge geometry of 1000 nanometers in a small geometry of 10 nanometers, right? So uh, because of this significantly different sizes, COMSOL sometimes will make your life very difficult, right? In that case you need to use user control mesh, and then mesh the bigger geometry separately, smaller geometry separately, but both have to satisfy this criteria, mesh criteria.
Okay.
Okay,
Okay,
Okay, sir.
Uttam,
so
Thank you.
I
yeah,
have, I have a question.
yeah.
My name is Faraz, and you know about PCB design softwares like Cadence, Allegro, and LTM. So
Okay.
what we do is that when we do the PCB design, these softwares also, like in LTM and Cadence, you can also check the impedance of the signals. It's there is a 50 ohm signal or 100 ohm signal, and you can simulate some simulated. Like you can check the signal integrity and power integrity of your PCB.
Hmm.
So can we and here you're telling us about the optics. So
Yeah.
this optics should be part of a product, or should be somewhere in a PCB. So we can also simulate our PCB designs in COMSOL, or here we are simulating also. When we are simulating it, we are also considering the temperature, what in what temperature is product is going to be used. All these things are also considered here in console. This is my first question, and second is that can we also simulate the PCBs here in console, the way you are right now you are simulating.
Yeah, yeah.
Yeah.
Yeah, definitely. You can model COMSOL as well, this PCB as well. So I will just show you.
Yeah.
However, with PCB, you don't need to use port condition. There is something known as LUM port. Okay,
Okay.
so so you need to use LUM port condition, and with LUM port condition, there are options of this impedance. Okay, of how
Yeah.
much you want to apply. So I will share you this link. You can just go through and visit few of these examples, application
Yeah.
model file. There are a lot of examples. You can see
Thanks.
PCB modeling and others. So either you model with PCB, or you model with uh, optical waveguides that you're talking. Eventually, it's just the electromagnetic field. So With PCB, when you're using lump ports boundary condition, which is not available with wave optics module, you actually need to apply potential like voltage.
Yes,
Okay,
yes. So,
instead
so
of applying modes, now you're talking about mode of propagation like TE
yes,
mode,
yes, yes.
TM mode, like axis polarized. So in lump port, we have to give between two conducting boundaries, the top and the bottom strip. We apply a particular voltage, and based on that geometry of your conducting conductors, it will actually create a particular mode, which is kind of fundamental mode, or a higher order mode using this numerical mode. Again, you can play around with those as well. So that depends on us, but yeah, both of them is possible. Okay, looks good.
Excuse me, sir.
Yeah, Jansi.
Hello, sir. I'm Jansi. Sir,
Mm-hmm.
actually, unknowingly, I used frequency domain instead of wavelength domain, so I got stuck. So,
Mm-hmm.
will the result will be same if
No
we
problem. So
used
if
frequency
no, it
domain
will be
also?
same.
Or?
So instead of in frequency, you just yeah, in the frequency you just need to write, because c equal to f lambda, right? So f equal to c by lambda. So
Yes,
the
sir.
way to write speed
Hmm.
of light is c underscore constant. So I'm just writing it in the, so frequency you just need to write as c underscore constant divided by LDA naught. Then you get the
Okay.
same
Okay,
if
sir.
you're using frequency domain. So f equal to c by lambda. Everything
So
will be
you are
same.
changing the wavelength. You are changing the wavelength. No, so where
Okay.
it is changeable here in this case for this frequency domain.
Yeah, it's in the parameter,
That
right?
means parameters only we can change.
Correct. So you can do a parametric sweep. So in the study one, if you can see my screen, if I right click on study one, there's a parametric sweep, right? So I can use my parameter to sweep that I will show tomorrow. So you just right click on the study one parametric sweep, and then the same parameter you can call and then
Yes, sir.
sweep. Then you can either use wavelength domain or frequency domain. Doesn't matter because you have defined frequency as c by lambda.
Okay, sir.
Okay, so
So
I
one
think
more
Kavita has a
thing,
question.
if
I'm use.
I am
Sorry.
working on
Mm-hmm.
plasmonics, so if I want to, so shall I ask or someone
Yeah,
else?
please go ahead. No, no, please go ahead. Don't worry.
Actually, I'm working on plasmonics. If I want to like make a different, let's suppose different size of spheres
Okay.
at the same time, because my particles or of these nanoparticles will be of different shape. Let's suppose from transition from prism to sphere. So how do I show the transition at one picture in this simulation?
I'm not getting you fully.
By applying some laser light.
I understand you want to apply use some SPR to kind of simulation you want to do, right?
Yes, sir.
Surface
Yes, sir.
plasmonic resonance you want to model. So instead of modeling the
Yes,
complete
sir.
geometry, you actually model only a single unit cell. So if you see this plasmonic example, have you seen this plasmonic wire example?
Uh,
So you can see this example. It's actually it's a very good example to start with.
okay,
So
sir. I'll
what
go
is
through
your
it.
question is that your the size is changing of this this
Size and
rods are
shape
changing, for
also
example,
changing, and yes, yes.
but it will
The
not
particles
instantaneously
are,
change,
let's
right? It's
suppose it,
like you have a,
yeah, time variant
okay, the
after
as
a
like
certain
what
time
is the
period.
order of time scales that you're talking about?
Let's suppose if I irradiate a laser light on a sample for, let's say, some 10 minutes. After initially it may be prism, later it may turn into something like slowly the particle shape is changing into finer, like sphere, something like that. That
Yeah,
that
but
way,
that
how
kind of
do I
transformation,
model
like
it?
Yeah. But this time dependent is difficult. But basically, you can do it two different models. One is triangular or space prism. Another is circular. So two different models you can create and see what is the S parameters.
Oh, okay, sir. Yeah.
Make two different
Thank you, sir.
geometry. Then yeah, that is the simplest way to start with. Another is to transform. From there, you can do multiple change in geometry deform. So then there is something was deform geometry. In that, you can keep on changing, deforming the geometry, right? But that is little bit more involved, so it may take some time. But yeah, you can still do it. Okay,
Okay,
deform.
sir.
Just Google search about this deform geometry in COMSOL. You'll get it. If you want to do instantaneously
Okay.
change it. Otherwise, one simple way is to use multiple models and then keep on changing the geometry accordingly. Okay.
In the same model, or
Uh,
should I like two different simulations, or within the same simulation model it can happen, or
Two different would be good to start with. As you best is to make it as simple as possible. So either you can make it two different model, or if you want to compare both the results in the same model, then you can make two different components. Here you can see, right, there are component one. I see this component one. Right. Similar to that, you create one more component for the spherical. Component one could be for the prism. Component two could be for spherical. Okay.
oh, okay,
Then you can
sir.
compare both
Okay,
of
okay.
them results together. Because
Oh,
here,
okay,
if you
sir.
apply one more
Thank you.
component, you can see this is coming over here, right? So but results there is only one. Okay, so both you do solve for both different components with two different geometries, and then you can compare both the results in a single result solution. Okay,
Yeah. Yes, sir.
you can try it out and you can tell me if you are facing some problem throughout these 5 days. We can
Yes.
see how it works.
Yes, sir.
Yeah,
I'll
hi,
try.
Sabita, you had a question.
Yes, sir. It's regarding Jancy's question, it's continuation to her question only. Actually, she is radiating with femtosecond laser pulses. So basically, she start with the prism shape. So in the nanosecond timescale itself, the shape of the nanoparticle changes to a more truncated. So it was sharp prism, then the tips are getting truncated, and it is going to a circular prism shape. So it is like a transient phenomena. So is it possible, sir, to do such? So
Yeah,
that's it.
means that is possible to do in COMSOL. Transient the time explicit study is there. So with that, you can do it. Only challenging is the how you change the geometry. So how to make the geometry changes, you have to use deformed geometry. Okay, so that deformed geometry is what you need to see. So you need to apply some mathematical um, uh, equation to mention how at the edges the deformation is going to happen.
So it
Okay.
basically a user-defined model we have.
Only the deformed geometry becomes the user defined. Otherwise, everything else is same.
Oh,
Okay. In one of the example, if you see the femtosecond Gaussian pulse, we have Gaussian. Uh, so it's a femtosecond Gaussian pulse, right? So transient Gaussian pulse. So this second harmonic generation was the one example. Uh, temporal. Temporal. What was that? Plasmonic nano array. This one time domain. So here it's a femtosecond Gauss temporal Gaussian wave which we are sharing. So this looks to be the more relevant. So you can go through this. So in this model, you're only interested in the source part. So you can just try to learn the source part from here and then implement the same thing in your model.
oh, okay.
Okay. So Kavita had a question. If I'm using optical fiber, then if mesh is user control, the value of n will be clad or code. Yeah, optical fiber will be doing it in the day 3 perhaps. Once that is the time, then I will talk about. So basically in optical fiber you're doing mode analysis, right? So mode analysis, you don't need to do physics control mesh, because modes of the optical fiber are not dependent on wavelength. It's a spatial parameter. So okay, so you don't need to, only the propagation you need to modulate um, with the wavelength. It should be a function of the mesh along the direction of propagation is needs to be lambda by 5. But if the cross section is there, the modes are there. The modes are kind of very big compared to the wavelength. So you don't need to have the lambda by 5 mesh requirement for the cross section of the optical fiber. But if I'm modeling the propagation, then yeah, lambda by 5 is required. Lambda by 5 by the refractive index. So if it is a core, it has to be lambda by 5 by the refractive index of the core. If it is the cladding, then it has to be lambda by 5 divided by the refractive index of the cladding. Both the domain needs to have different mesh settings. Yeah, for SPR we want to transmission coefficient. Transmission coefficient, one of the way is to create S parameters, and as I shared some time back, plasmonic wire gritting, you can see that example over there. How do they calculate S parameters, scattering parameters? Yeah, it is the same as scattering parameters.
Hello, sir.
Yeah.
Uh, yeah, sir. Actually, I have a question. Like, we can add two multiphysics like stress means
Yeah, you can do
and
that. So,
wave optics.
yeah, one of the example is stress optical fiber. So
Okay.
I can share that it couples. So what physics you want to couple?
Means wave optics and stress.
Okay, yeah. So this is the example then that you can couple.
Yeah,
Okay.
here actually they have used PML, like they have
Mm-hmm.
defined like PML and give the some defined refractive index based on
Okay.
the bending.
Okay.
So I need like simultaneously they use. It is possible here. Means it can stress the optical fiber, and at that time we can see
So you need
the
to do time
coupling.
dependent thing then you need to do.
Yeah, yeah.
Yeah. So that is the way that you need to approach is time dependent, the time explicit. Electromagnetic wave time explicit you need to do,
Mm-hmm.
which is difficult. Means then you need to see this time domain modeling, this dispersive Drude Lorentz media. This is time domain modeling. So, but working with time domain is very difficult, especially with light, because the time scales that we're talking about is in order of nanoseconds, right? So
Okay.
femtoseconds actually. So it becomes very difficult to resolve, or it's very time consuming. So
Actually, in this case, that we need to know the how much refractive index is changed due to the stress. But
correct.
I need that actually simultaneously the system give,
Yeah,
then it will be
that's
better
quite
for that.
challenging. Yeah, I understand it.
Uh,
Yeah, but yeah, means you can try it out. Means
and I have tried. Actually, I
hmm,
cannot get any solution.
okay, yeah, yeah, I understand. It's
Mhm.
really involved a problem. Yeah, time dependent is very involved problem. Yeah, I
Yes, yes.
understand.
Okay.
Hmm.
Okay.
Okay. Any more questions? Anyone have?
Sir, one more question. Just
Okay.
actually, so non-linear thing can be done in the console.
Yeah. So I will share you the blog.
I have
Uh,
seen, I think.
you've seen that blog. Okay.
Which blog?
So doesn't your question gets answered through that blog?
And, actually, I want to some second harmonic generation in some photonic crystal.
Okay.
So, what a modern onion. Okay.
So second
Yes,
harmonic is
I have
also
seen your blog. Yes.
okay. Yeah, in this I have discussed. Well, this is just very basic stuff that we have discussed here. So
Mm-hmm.
it's not much in detail, but yeah. So it's second order and third order effects we
That I
talked
have
about.
generated.
Hmm.
Yes.
So in plasmonic you want to model.
Mm-hmm.
Mhm. So what are the challenges that you are facing?
Like you see, there is a photonic crystal. So there are some periodic holes are there. Okay, so we need to change the which we need to give some non-linearity of that photonic crystal so that they can give the second harmonic. So how
Okay.
we can give like
Okay.
by uh,
So what we can do, you can just formulate it. You can make it in some kind of PPT in the day 3 or day 4 if there are not much questions, and one on one you can share your model, and we can
Okay.
see if we can see
Okay.
we can get through this thing. Okay,
Okay, sir. Okay, sir. Thank you.
looks good. Okay, looks good. So
Sir,
Kavita has one more question. Jancy has one more. Yeah, tell me.
sir, actually, instead of air medium, I want to use water medium. So, what kind of
So just only
how
the
do I
refractive
use?
index changes. Refractive
Yeah,
index changes. So here, if you can see my screen, the air has a refractive index of 1, right? So
yes, sir.
what is the refractive index of water?
1.3.
1.3. You can see the
33.
water is here in the part of over here. So you can check. Okay, it's not, but refractive index is not there. So you can just see what is the refractive 1.4. I guess I don't remember exactly 1.3 or 1.4. So just change it to 1.3 or 1.4. That it becomes water.
Okay. In the same air domain.
Yeah, correct.
Okay.
Yeah. Okay.
Yes, sir. Yes, sir. Thank you.
Kavita has a question. Can we model heterostructure optical fiber? I think, yeah, we should be able to model, but I don't know exactly what is heterostructure optical fiber. Okay, multiple layers of optical fibers. Still a mono or multiple mode of fibers. Okay. I think it should be possible. Means I have not tried it out, but because it's physically very looks to be possible. Single mode. Yeah. Yeah, this should be possible. Yeah. I'm not seeing it, but yeah, I see. I think it should be possible. It should not be because it's just a multiple layers of optical fiber. It's just about how you set up the model. Okay. So I think optical fibers we'll talk about the third day. So third day. So you can discuss at that time. You can create multiple layers and see. U-bend optical fibers, yes, that should also be possible. The only challenge with optical fibers is the propagation distance. So if you make very long distance of optical fiber propagation, you require a lot of memory to solve for, right? So 3D domain and all those things. So that is the only challenge that we face. Otherwise, it's not a big problem. Mm. Even though it's like in order of micrometers, but you even modeling 1 mm of the optical fibers becomes very difficult in 3D. Okay, so that's why people ideally use simulation tool to understand the mode of propagation of the fiber multi-cores optical fibers. Okay, yeah, you can share your design. We can try to understand different approaches to model. Okay, looks good. So that's it from my side today. I'll share the video recording in some time, and let us see tomorrow. Okay, take care. Bye bye.
All right. Thank you, sir.
Yeah, thanks. Bye.
Thank you, sir.